Okay, we begin. So I think the professor wanted me to get signed signatures, attendance. I don't know what the drill is, but just feel free to circle this around. Put your name, your ID, and your I think email address. I don't remember. But whatever I should do. Okay. So welcome one and all. Thank you all for coming in today. I know it's after a vacation and everything, but all of you made it. You guys were promised a lecture, a guest lecture specifically on reinforcement learning. But as you can see from my topic, there is no reinforcement learning. There are a lot of big buzzwords that walk you through it. But nonetheless, there is no reinforcement learning, right? So you've been completely scammed. So throughout the entire lecture today, I try to keep as much buzzwords out as possible. That's a promise, right? So I will never be using the word AI. Probably the last time I'm using it, right? Because at least given the background, whatever you guys have been trained, you've been exposed to is optimization. Right? Let's stick to that. Right? You have some cost function, you have some objective, you want to maximize something, you want to minimize something, right? And deep reinforcement learning is just fancy jargon in a certain sense to the same exact thing. Okay. Okay. So before I get into the concepts, I try to keep this more presentation style and less lecture style, right? And it's more of a tease of the concept. So the agenda of this lecture is not to make you guys from zero to hero. That's not going to happen, right? It's because you need to it's a laborious process to get the math and everything right. But it's going to give you the right amount of tease for the concept to get a feel of it. And the primary aim is to build a strong enough intuition, right? So for example, the next time you see the reinforcement in math or the code or whatever, right? You just don't get scared, right? So working intuition is all that is the hope of this lecture for today, right? And at any given time, if anything is unclear, feel free to just hop in, just throw a question. If it's something is unclear, it's probably because it's unclear to me as well. Like if you don't understand, it's probably because I didn't understand it well enough. So just catch me in the act, and then we can have a discussion, and we can all understand it a little bit better. And whenever I give a lecture or whenever I talk about something, people are always distracted, taking photographs of me or the slides or taking notes. If it's your style, it's totally fine. Feel free to take the notes, but not at the cost of missing this overall lecture. And this QR code right here is exactly for that. Just for the people who want to have notes, all this notes is going to be available to you. Just scan it. You will have it in your screens. Okay. So one final disclaimer would be, this is going to be more like a roller coaster ride, right? So all of you need to strap in, but you need to stay with me. Okay. So there is no, we will have breaks and everything, all that is there, but don't get carried away by the details. Just look for the intuition, for the concepts, whatever we're trying to actually learn here, right? Okay. So that said, let's begin. Let me first unpack this topic, right? Empirical policy optimization, a deterministic, stochastic perspective for robot control. Too fancy. Okay. So the first word, empirical policy optimization. What does that mean? So the empirical simply means that we're going to use data, right? We're going to use experience to somehow optimize our policy. What's the policy? A policy is nothing more than a controller, right? So what you guys are familiar with, MPC, PID, whatnot, we want to somehow optimize it, somehow tune it, somehow make it like, do optimal things. Okay, so this is something you guys know, optimal control, where we're asking the question, can I optimally control a given system? Right? It's a very clear question. It's a very clear formulation, right? And we have seen some practical applications as well. And recently, people in the deep reinforcement learning camp, right? So that's this other side of the fence. They're asking this question: can I learn a solution for any problem? Right? I've intentionally kept a little vague here. Any problem in the sense that it's a decision-making problem, but still, can I learn a solution for any problem? Right? So the difference here is slightly nuanced. In the sense, they're not interested in things like absolutely great performance or trying to do something that's not done before, but the whole aim is a little different in the sense that can I even learn a solution, right? So that's the intelligence and learning side of things. And where empirical policy optimization lies, okay, is somewhere in between, where we are still interested in getting an optimal policy, right? So my perspective, or throughout this entire talk, the perspective is gonna be, can I learn to control a system to do anything? All right. So what I'm trying to say here is, I am definitely going to learn a controller, but then I don't want to restrict myself to a specific task per se. Okay. So you guys are familiar with the MPCL walking controllers that you guys developed in this course, right? It's really optimal at doing something, which is walking, right? But let's imagine I want to make it do backflip, all right? The controller is not going to work right out of the box. You need to think something different. So that's the nuance here. So that's exactly what we're intended for. You want to learn a controller, but for a specific system to do anything. Okay, so that's why I'm calling it empirical policy optimization. So the next part of the topic was deterministic and stochastic control perspective. All right. So what I mean by that, so the word there is stochastic. I just take my word for it, right? So up until now, in being in the Department of Mechanical Engineering and whatnot, we knew this guy Newton. He said F equal to ma, and that's it, right? So all the models you guys wrote was just saying F equal to ma, which is deterministic. Meaning, if I tell you the current state, then the next state is exactly what the next state is, right? Because you just compute F equal to ma, and then you get the next states. But then there is this alternate perspective where it can be probabilistic, right? So think about any process where the next step is just a distribution, right? There is some probabilistic notion to it. I'll explain it a bit, but let's just look at a little bit of a history here. So from both these perspectives, eventually what we're interested in is to control hybrid underactuated systems, right? So what is this big word? Hybrid, in the sense that we want systems that can jump, like their states can jump. Think about a walking robot. Every time you make a contact, the velocity is jumping, right? Underactuated, which is the number of actuators now is less than the number of states, right? And if you don't like the name, it's just going to be all interesting robots. If you ever think about any interesting robot, it's going to be a hybrid interactuated system, right? So now let's look at the deterministic side of the story, right? It all started in the 1800s when none of these people are controls. They're all mathematicians, right? They were looking at parts of the problem. He came up with some really, really beautiful theories, right? So specifically this guy here, he was not even interested in the control problem. He just wanted to know why planets were stable, like, in stable orbits, right? And then, however, in the 1900s, the engineers kind of picked up. They had like actual engineering problems in mind. So that's when the amazing PID was invented. And the guy here, Joseph LaSalle, he looked at this old theory and made it more, control friendly, right? And then in the 1950s is when people are really thinking about optimal control, right? So let's say there is some controller, but how can I make it minimize or maximize the cost, like some design considerations, right? So LQR, probably you guys saw in the course, and Pontryagin's maximum principle, And then 1960s, he landed a man on the moon, right? There were a lot of an explosion of control research, right? So all these techniques, the passivity, sliding mode control, to name a few. So the whole point of it being present here is to give a historic preview, not to explain or anything. But something very interesting happened here. So up until this point, people were interested in only getting a controller for a nominal system. What I mean by that is, let's say you write the map, F equal to ma. You found a controller that will exactly control your system, which is F equal to ma. But what happens in the real world? Is the real world F equal to mn? I don't know, right? So let's say you write some equations or some controller for your walking robot, or let's say a drone, and then you go take it out in the wild, and then there is a strong gust of wind, right? So let's say there is strong air, right? Uncertainty. My F equal to ma didn't have that, right? Which means my controller is going to fail. So people, when they actually apply to real world scenario systems, that's when they got to know that nominal controllers are not enough. Okay, so that gave this dual notion of adaptive and robust control, right? What will I do, or what should my controller do in the face of uncertainty? Okay, so I'm not so deterministic people actually were thinking about uncertainty, right? So they were thinking about what happens when we are out of our models, out of scope of our models, so to speak. Okay, but this exactly is when people are not very satisfied with the answers that they got, right? So they had some notions, but they always traded off performance. They were not very happy. They were not very happy. Okay. But then in the 2000s, this is just for, again, once again, for a historic review. This guy, he was a full professor already, nonlinear controls. Guy used to do differential geometry for a living. So he took a sabbatical, and then he decided, I'm going to make robots work. Right? And then he came up with this very, very elegant math called hybrid zero dynamics. Right? And till date, this is one of the most elegant understanding of the math of work. Right? If you want to really, really get to the understanding of how a machine should walk or how a man should walk, the math kind of ties it all. That was hybrid zero dynamics. And his student was the one who made it into practical controller. So that was this notion of CLF, right? So they use CLFs and QPs, something that you may have seen. And then they made these really, really beautiful walking machines, right? Back in 2000s, where I. This is just existent. This is Kaushal Srinath. And his students' class is what we were taking, and I'm that fellow student. Right? So that's like a academic lineage. So of course I'm biased when I say it's beautiful, but. And then in 2010s, people were also thinking about safety, right? So there was this thing called control barrier functions, really, really cool stuff. I'm not going to get into the details, but this one. Okay, so we do have reasonable solutions, right? So now the question is, why do I even need a change in perspective? Before we answer that, on the stochastic side, who are working? So do note that all I've listed here are methods or theories that I think will eventually lead to controlling the system, right? And as you can see, there is just one guy. So that's why his picture is bigger than everyone else, right? Because there's literally one guy there, right? And we will meet him soon down the lecture, right? But in 1950s and 70s, he was talking about stochastic optimal control. How can I have a better treatment of uncertainty? How can I model uncertainty in a more natural way, right? So we look into it. There were some nice works, right? So this guy is talked about the same optimal control, but in partial observability, right? But yeah, that's all the theory that there is. And whenever people were thinking about applying it, it was not very straightforward, at least for the task that we are interested in, which is what is going to be the primary aim of today's lecture. Okay, so now I think we can more concretely ask, why the hell should I change my perspective? Especially because the state-of-the-art deterministic control, or MPC, is able to do all this already, right? We are backflipping. We are able to manipulate our environment, right? Whatnot. We're able to do that. I cannot do that, right? So why should I even change my perspective? So any guesses? Like, I think you guys have kind of got your hands dirty with these methods. Any guesses? What is like unsatisfactory with this? I mean, it's very satisfying, don't get me wrong, but
I mean, I imagine each individual motion has to be very finely tuned to that specific motions, perhaps.
you're right. But stochastic is not going to help you in any way. You're going to tune always. That's the
uncertainty, and probably another would be the computational efficiency. Like the more dimensional your system is, the more and more complex it's going to be to solve.
That's good. That's a good one, right? For sure, because you see this backpack. It's not that by design the people wanted it to look like a hunchback or whatever. There are 3 computers running online, right? And they are munching numbers really, really fast. Like, it's able to compute the complete dynamics, what you guys would probably do as offline trajectory optimization online. And that's why it's able to do this flip. That's right. So that's a totally right point of view. But again, once again, I don't say that stochastic is going to help you there in any way, or it's very arguable, right? You can always get a lightweight controller. You can always make stochastic controller arbitrarily heavy.
Is it because
I guess robots are more useful in like the real world, whereas this is kind of a controlled environment.
Again, these are things even I didn't make notice of. I think that's exactly right, right? So, quote unquote, this is choreographed, is what he's trying to say, right? These videos are taken by Boston Dynamics themselves. So let's say one day I walk in with my camera being a jerk and I try to record them. This is not what you will be looking at, right? That's what they will be very, very unhappy if I do that. And that's same for our lab as well. You come into our lab someday and then you come in with your camera, you're not allowed. Okay, yeah, so that's totally right. Okay. But the answer that I have is something that I feel boils down or takes all these perspectives and brings it down to its bits. Okay, so here is my answer. So there is not so good answers, or at least the deterministic point of view doesn't give us very good answers. When you think about discrete decisions like contacts, what do I mean by that? Try to recollect how you guys wrote your LBC. The business was always like, you give me when to contact, right? Like food placement. You tell me when to contact, and then as an MPC, I'm munching numbers for your force, right? So let's say if I tell you that you one leg is in contact and the other is free, you can do decisions on where you'd like to place the foot or probably the contact forces, but you cannot decide where to contact. Discrete, right? So what you guys probably did is to think about gates, because walking is essentially a cycling behavior. You are periodically making and breaking contact. So you guys came up with a heuristic. But see this guy, right? Where is the gate there? Okay. Forget gate. Where is the ground there? It's defying gravity. You can, if you had seen this instead of the apple, there is no gravity to it. Trust me. Okay. So what I'm trying to say is, it's a very mutual, a coupled problem. You cannot decouple it and say, hey, you tell me when to contact, and I'll compute the forces for you. That's not going to work, right? And this right here is exactly what it is doing. So here, for example, in this setting, you see, the designers explicitly tell it, you can have a contact here. That's why if you see the foot, the hand is like pinned, right? But then the MPC fills the other things where it decides what the forces should be and everything. But you see this pin joint, it's almost like a pin joint. They tell you this is where you contact. Nobody is telling that guy, trust me. Okay. So we don't have a good answer for that. Like you cannot co-opt. So in a way, what the current deterministic or current MPC is doing is it's solving a sub-problem where it's outsourcing the contact decisions and it's just computing the forces. Okay. So the second one is the need for an explicit and optimal state representation. What do I mean by that? Right. So here, if I ask any of you what the state space is, it's very clear. The positions and velocities of the system, right? Center of mass, joints, whatever, but positions and velocity. Second order system, you've all seen it. Now let's assume I have an infinitely dexterous hand, a robot, and I want it to do that, which probably everyone does, in their home every day, right? Through a vegetable, you can cut it. Now my question is, what would be a state representation for the capsule? I mean, serious question. I don't know. One of my students asked me, I said, I don't know, right? Is it a rigid body? Of course, we can always approximate. You can say, yeah, every time you cut, you get a new rigid body. But then think about the cutting problem itself. When you cut the vegetable, you're not worried about the position and velocity of each part, so to speak, but you're interested in the tactile feedback. Like even if I blindfold you, you guys will be able to probably cut the capsicum really well because you have an implicit state representation that you cannot write out as an equation, right? So the need for that is very, very limiting. Okay? And the third one is this notion of raw robustness and reactiveness. I think the best explanation for this could be a video more than any of my explanations. Okay, so see this guy. So very pixelated because it's an old video. Sand, slipping, friction, everything has left the chart. So it's just the cheetah. It doesn't even look at the ground. It doesn't even care. Okay, because it's this blindly robust and blindly like reactive. Yeah, and it didn't end well for the gazelle or whatever that is, simply because like it's also a fantastic mission. It can also do all these gates. It can be very agile, but it's not as robust as the cheetah. Right? So if it stumbles, then that's game over. Okay, but what I'm trying to say is these are behaviors that I cannot explicitly write an equation, or I cannot like pump into my optimizer, my QP, and I ask, hey, give me that, because I myself don't know how what exactly is happening there. Like it's really robust in the sense the cheetah never looked at the ground to decide, hey, this is where I need to plan to place my foot. It's just blindly robust. That's what you're in capture. Okay, now the question is, who said Boston Dynamics is not good at this, right? You should not take my word for it. So that's the next part, where if you see, it's the exact same video. By the way, I'm not being, a bad guy or a jerk here. They outsourced the video. So what happened there? What happened there? Look at it closely. The moment the contacting hand slip, all bets are off, right? So if I were in that position, right, maybe if my hand slipped a bit, I would immediately try to place a better contact, right? I would immediately try to come up with a better contact setup, but MPC was not able to do it, right? And the second thing, which is even more sad, is you see that. Forget the cheetah, a little bit of a slip, and then you go all the way down, right? So we lack that raw robustness that I was talking about, okay? And moreover, in this setting, the foot is sliding and the mud is like, slipping and whatnot. We don't even, our poor controller doesn't even know that all these things are happening because that's not there in the dynamics. It's unmodern, right? So that's exactly why we need approaches that can do this. Okay, now let me show you another state of the art. Yeah, a lot of videos. Look at this guy. Yeah. Right, this is a robot. Just won't fall. Yeah, what is the state space here? What is the contact sequence here? I don't know. But if I say my task is to just locomote in this wild setting, I think the controller is doing a perfect job. Is it optimal? Is it stable? Is it safe? I don't know. But is it solving the task? Oh, yeah. Right? So it doesn't care. There is slip, there is whatever. And of course, mean roboticists, hitting and whatnot. Yeah, it's a really nice video. You guys can watch it fully. I think this specific one is one of my favorites. You see that? Yeah. No foot. Okay. Blindly robust. Raw and robust. And the next video, probably a little less, intuitive, is this. So maybe let me pause this for a minute. Okay. So here, let's say I give you this robot and I give you this task. The task is very simple. Just spread the sauce, right? That's all I'm saying. I just want the sauce to be spread over this. What would be a solution that you guys can throw in? You guys are all roboticists. You've seen enough robots now. Any solutions? Any guesses? It's a manipulator, so PD control is all you need, right?
Just just go in circle motions from center to up.
Yeah, that's exactly what I would do too. Yeah. So I would say I will have a circular trajectory. I'll do inverse kinematics and then spread it. Why? We don't need 27 billion parameters for it. We don't need ChatGPT super intelligence for that. We just need IK. Let's see what happens right now. That. Okay. The moment that happens, what happens to our IK-based solution? Okay. We said, yeah, do circles, but then there is uncertainty, there is perturbation, whatnot. Right? You can still say, okay, I will try to somehow estimate the center of this, whatever this yellow thing is, and I'll kind of spread or whatever. But you see, the task was not that. The task was not to track a circle. The task was to spread the sauce, which means your controller should actually understand what a sauce is, right? And what does it even mean to spread a sauce? Towards the end, what I care about is whether the sauce is spread well. I don't care about whether I'm tracking a circle really well. That's just important. So here, if you see these robots were trained in a way where you give all perturbations you want, it always ensures that the sauce is spread well. Okay, simple enough, but not that simple. And it's able to just look at the raw images, and it's able to come up with this policy all by itself. So these two are examples of learning, which is exactly what hopefully by the end we'll be able to do today as well, right? So on that note, let me give the outline for the lecture. Okay, so it's going to be 3 parts. So the part 1, we are going to look into stochastic optimal control, right? All the fun time is over, I guess. All the videos are done. Now we can dig into the math a little bit. We have stochastic optimal control, dynamic programming. We look at it in the finite space and finite horizon settings to really build the intuition of where these magical algorithms come from. And then we'll venture into reinforcement learning, right? Where we'll actually look what the difference is. So I said we need stochasticity, but then we need is stochastic optimal control. Why do you need learning, right? Please look at that. We'll exactly see why that's needed. I'll once again demonstrate in tabular settings. We'll code it. Okay. And finally, in part 3, we'll eventually look at the absolute pinnacle of reinforcement learning, the one that trained all those robots as well as your ChatGPT, right? And then we'll see how these algorithms work, and then we'll try to code that as well. So if I give a high-level overview of the outline for today, you'll have a stochastic perspective first, and then I'll give you the learning perspective. Finally, the scaling perspective, how to actually get it work in the real system. This unfortunate and the mixed thing about this is the rigor in that theory decreases, right? So here I can make statements that you are controller is optimal. Okay, you can sleep peacefully at night. But here I cannot tell you that. One day it work, one day we don't know, right? But then the coolness in practice increases. So follow the arrow, right? You're gonna get all those videos that you saw right there. Okay. So yeah, so I think we have like 3 hours maybe. Between each of these parts, I'll take a break or something. Just let me know if you guys feel it's like too much or anything. We can always take a break. It's like well-spaced lecture. Okay. Part 1, stochastic optimal control. Okay. Since you guys have a background in optimal control, like MPC and whatnot, I thought the best way to introduce this is part by part compare with whatever your deterministic is doing. Okay. What is the first thing we need? A state space, right? So without the state space, I don't know what is what. I don't know what is even optimal. I don't know anything, right? And that is something that both of them agree. Yeah, we need state space. The control space, the same thing, right? Like if there is no control space, what am I even trying to compute? Then the transition dynamics. This is where things get interesting. Yeah. This we all know. And love, right? Newton gave this to us. You're in state xt. You applied control ut. You go to state xt plus 1. The dynamics, discrete time dynamics. And the other side has something weird, PV line. So here also, you are in state xt. You apply ut, but then something happens here. What is happening there is all but it's saying that even if you are in state xt and ut, and you completely know all that, your next state is not a single point, but it's a distribution. So that's how we are capturing the uncertainty. I'll give a more concrete example in a bit, but that's the first difference between the stochastic and deterministic side of optimal control. So the next difference is in the objective. Okay. So this is something that you guys know, where you say there is some trajectory, some MPC, something, right? We don't know. We have per stage cost. We sum it over. We have an integral over time, right? And we want to minimize this guy. But see the equivalent on the other side. It's still the same thing, but there is an E there. So for those who know the probability in math, bear with me. I'm being very, very simplistic. But all this is saying is, on an average, I want this cost to be minimized, right? Just stick with this idea. I'll explain it in a bit. With that, the methods that exist, there are 2 approaches. One is an open loop approach, where you still essentially solve this problem, but you're only interested in the control as a signal, right? So what I'm saying is, let's say think about your MPC, you have an initial condition, and from that onwards, you're just interested in U as a function of time, right? You don't care about it being a function or a closed loop system per se, you're just interested in a sequence of actions. Okay? So with this, both have really nice formulations, right? But if you think about your QP or the MPC that you did, they probably fall in this category. But that's not the only approach. You can also have a closed loop approach, where you're still solving the same problem, but now you're not interested in a sequence of control, but you're interested in finding a function. A function, if I throw in the state, it's going to throw out control. Or, in other words, I'm interested in finding a function phi, which in every state of my system is going to tell me what is the optimal control is. This is different. This we know how to solve. We plug it into a QPL and LP, you're almost always going to have a solution. But here you're searching for a function. What is the space? I don't know. So you see, this led to all these nice theory and everything. But on practice, we do this. That's what we're going to look into. Okay? Any questions by far? Okay, that's good. Explaining it really well, I guess. Now let's look at these 2 guys. The only difference in stochastic side of things. Let's open them apart. Okay. Transition dynamics. We know this, right? So you probably met this guy. His name is Hector. He was here probably last week, I guess. So here is Hector trying to walk in this ground. Okay. And from the current state, let's say somebody gave me a fixed control, like somebody gave me a signal that I need to apply on the system. Okay, I'll apply it. And that led to this trajectory. Okay, so starting from this state, I'm applying this control. And if you just propagate the system, Newton tells us this is the trajectory you're gonna have. Now let me tweak it a little bit. And I'm gonna say, in this patch, somebody spilled something, oil, some fluid, I don't know, right? But that immediately changed the friction in this patch of the ground. Okay. I don't know what the value of the friction is. I never measured. I have better things to do in life, right? But I can tell you, it's in the ballpark of 0.2 and 0.6, right? Meaning the friction can be randomly some value in this range, right? This is all I know about the problem. Now the question is, how will I model this in this framework? Right? So this function doesn't allow me to incorporate this information, right? But I want a better way to model this. I want a better way to include this in my controller. So that's where our transition dynamics comes in. Yeah. So what it says is, that's okay. So up until this point, there was no uncertainty. It was f equal to fxt, ut, whatever. But at this point, at this state xt, if you apply control ut, you're not going to end up in a single trajectory, but a set of trajectories, right? Because depending on whatever the friction is, you will end up in a totally different trajectory, right? And that's all that I'm calling as the transition dynamics. It just says you are in state xt, you're applying control ut, but you can have a set of possible trajectories that you can end up with. These guys specifically. Okay. So that's stochastic, but this is not very useful, right? Like, what is this? How will I take something that I know? So this is something I know. You can write the equations. Anybody can write the equations. But how will I construct something like this? I'll give you one way, right? So still take your old dynamics equations, but now put in the friction and sample the friction. Now this is a valid candidate for your stochastic dynamics because you see the dynamics is deterministic, but the friction that you put in is going to be sampled. So together, it's going to end up qualitatively in something like this. Meaning at that point in state, you will have like a bunch of trajectories, right? So that's the first difference. There is one word that you guys should know at this point. Still, our whole notion of causality and everything is intact. What do I mean by that is, my action at u at state x is going to still affect all these trajectories. It's just that instead of a single trajectory, there are just a bunch of them. Or in other words, this dynamics is Markovian in the sense that the future state is only dependent on the current and not the past. Okay, so this is weird. We almost took this for granted, right? For example, when I write this for my dynamical system, you see the function or the next state xt plus 1 is always just a function of xt, which made sense to us because we come from a physics background, right? But is this a sufficient model? Maybe not, right? Like, for example, take the effect of battery discharge, right? So the rate at which your battery is discharging does not just depend on a current state, but a history, right? Whatever currents that flowed probably 10 steps back in the past, right? Think about mechanical wear and tear. So I'm running the robot today and something went out, some screw came out. And then I come back today, assuming still my system is Markovian, but the screw is loose. So I should have accounted for the history. Somehow I should have taken into account a history of states or measurements or whatever. And finally, time delays. Right? So if it is time delay, if any of you have seen the math, it's just an infinite dimensional problem. So the Markovianness is necessary for the stochastic optimal control problem, but more realistically, we may need more, but not for now. Okay. So that's the transition dynamics. The second thing that was different was the objective definition, right? So in the deterministic, it was just the sum over the stage cost. Or,
I have a question.
Yeah.
Can you go back to previous one?
Uh-huh.
In both cases, you need dynamic effect of.
yes.
But then, what will be the advantage of stochastic approach?
Yeah, because you're not seeing the approach yet.
Yeah.
Okay. This is I'm just setting up the problem so all of them are comfortable with notation.
Question. So you mentioned there's a difference between like non-Markovian and Markovian. Isn't your state dependent with your previous state? So indirectly, isn't your next state also dependent on your previous state?
Not necessarily. So the assumption you're making is that the current state X has all the information that was carried at until now, right? But if I chose a state space, so think about, let's say your positions and velocities, it tells nothing about the battery discharge. So if you choose a state which is battery discharge, then yeah, you're right. If not, okay. Good questions. Make sense? Cool. Objective. Okay, we had like a sum of some cost we want to minimize, and then I put this so-called E there, right? So what does it mean? Okay, this the way you spell it out in language is expected value of the additive cost. Okay, let's break it down. So the one on the top is nothing but additive cost because it's self-explanatory. You're adding the cost at every step. But all that is different in a stochastic sense is that the expected value is added to it. That's the E, right? What is an expected value? So all I'm saying is, if you think about this cost term, and I keep the same for stochastic, then it's meaningless because you see from this stage, there are so many trajectories. What does it even mean to minimize this additive cost for each trajectory, right? Because to be honest, there are infinite trajectories. We don't even know, and we cannot even minimize over all those trajectories. So all that this is trying to say is, all we care about is roughly on an average over these trajectories, I would like to minimize this cost, right? In the sense that if I take an average of all those trajectories and then I compute my integral over it, then I would like to minimize that cost, right? So a good way to think about this is on average, that is what it's doing. And for those who are interested in the definition or to actually know what is happening in the E, this is what exactly it is. So let's say X is some random variable, then the expectation of it or an average or whatever is just the integral over its distribution. Continuous and discrete, not important. If you are happy with the notion of on an average, let's go with it. But for the ones who need the definition, that's what it is. Okay, that's good. Now we have kind of looked into all the elements of each of this problem. Now let's assemble it back. So the stochastic optimum problem is just, okay, you've probably seen this exact structure before in an MPC, but with just not the tildes. So we want to minimize the expected value of the additive cost subject to Markovian transition dynamics for some controller pi, which we don't know at this time. I'll explain in a bit, and then over a distribution of initial conditions. So this is the problem we'd like to solve. Easier said than done. Okay. Why? You see, our search is over a space of functions. How do I even go and search for an optimal function, right? So enter this guy. So the man behind the math, one of our own, it's Richard Bellman, right? He was a professor in math, electrical medicine right here in USC. Okay. And at his time, I think he was one of the, so I think that's the father of dynamic programming and all that. So he wrote the algorithm we're going to talk about, right? And he was in the Manhattan Project. So he made the nuclear bomb and whatnot. I mean, computed for it. And one thing that struck me the most is he finished his PhD at Princeton in 3 months. When I was here, I'm a PhD by the way. When I was here in 3 months, I didn't know how to enter my lab. I'm being very frank. Okay, all the security codes and whatnot. But he did that. What I'm trying to say is this man right here was very, very rigorous, a very talented, blessed mathematician. And at that time, pure mathematicians used to look down on applied problems, right? They want to stay in the differential geometry land, you know. They want to do these abstract things that none of us will get. That's okay. But he took the bold step to actually look into applied settings, right? Which is amazing, in my opinion, if you think about a man of his rigor, right? So, yeah. So there is this one fun story about why he calls this dynamic programming. So apparently he was working for the military, of course, right? So he was developing all this math that we're going to look into. But then the people in the army were very, very pissed when they heard the words like optimization or mathematics research, operations research. These are all the terms that were used. So he said, you know, how can I name my research something so that I don't lose my funding? So he said, okay, programming sounds fancy. Dynamics sounds fancier. Let me put that together. I cannot go wrong. He was right. So that's the story of dynamic programming. So before we venture into what he said, there is this one quote that really struck out. Yeah. Because that is something that I didn't expect from him, right? Like, because I thought mathematicians' brains work differently than engineers, we don't tinker or whatever. But this is his philosophy. He said, the trick that one learns over time, or basic part of mathematical methodology, is to sidestep the equation. Forget the equation for a minute, he's saying. And then focus on the inherent structure of the underlying process. Okay? And then submit to catechism. What he's trying to say is, hey, I know all the math and everything, but sidestep it. Think about actually the process. Think about do these equations make intuitive sense? Do my assumptions make sense, right? What are the effects that I ignore? What are my state space should include, right? Those are the real questions. And then the theory will emerge. So this is the philosophy which I'm going to take the next step. here, right? So if you see fancy math and whatnot, stay with me, right? Because I'm trying to build an equation here. Ask me questions, right? Questions like that, right? Sidestep the equations. Okay. With that said, this man gave just one thing, Bellman's principle of optimality. Okay. Probably the professor mentioned this in the course. I'm not so sure, but this is what it is. Means nothing to me. Okay. The optimal value from K, the optimal value on the next step and the next step. People tell this to you all the time and expect you to understand magically. I never got it. Yeah. So I put a cartoon, which I think makes most sense to me. What Bellman said is, or at least the principle of optimality says is, so let's say starting from point x naught to point xt, there are infinite trajectories. And I'm interested in finding the optimal trajectory. Okay? Optimal. Then he said, or the principle says, if I now take a point xt on the optimal trajectory, then the sub trajectories x naught to xt should be optimal, as well as xt to x capital T should be optimal. Or in other words, if I take a point and I take any sub-segments of the optimal trajectory, they should be optimal as well. Does this make sense to any of you guys? Make sense? Really? So these things get thrown at me all the time. Any tail of an optimal trajectory is optimal too. Okay? Yeah. If xt belongs to the optimal path, blah, blah, whatever I said right now, so this is the optimal path, and I took a point, then this segment and this segment are optimal as well. What's the big deal? It's an observation, right? But why is it any useful, right? It's more, nothing more than observation, in my opinion. But the brilliance of Bellman is this observation or this principle led to a set of theories, which is really fine for a mathematician. But he took it a step further and made it into a tangible algorithm, not something you see in all these mathematical discoveries. Okay, that's the brilliance of Bellman, in my opinion. Right? Yeah. So now let's go look at how to actually apply this so-called algorithm or this principle. Okay. So before we get into it, we have like 2 stops to make. We are like kind of defining the problem a little bit better, so we can apply the algorithm. So the first is, instead of thinking in the continuous space, we'll be thinking in discrete space. Why, you may ask? Because things are finite. As humans, we can very easily think about finite things, right? Think about the number of tables and chairs here. Think about the number of students here. You can count it. You can enumerate them. 1, 2, 3, 4, 5, 6, 7, 8. But then now I ask you to think about real numbers. I think about, infinite of them. It becomes really hard. Right? So we'll restrict ourselves to the finite setting, right? Or in other words, the state space, there are just finite of them. There are n states, right? Which I can always list and enumerate them. And then there are m control actions. Okay, that's all. So all I made is to take the space and make it discrete. And the transaction dynamics is as before, the thing that I talked before. Maybe this was very clear in the example of Hector and whatnot, but the tabular sense, at least the first time I saw it, it was really confusing. I couldn't visualize this. What does this P look like in the tabular setting or the so-called finite setting? When I make the control and state finite, what is it going to look like? That's what it's going to look like. Okay. Let me open this up for you. So let's say you are now let's assume that n is equal to 4 and m is equal to 3, right? So there are 0, 1, 2, 3, 4 states, and 0, 1, 2, 3. I start from 0 because I don't do MATLAB. Okay, so that's why it's 0. But nonetheless, it's the same. So there are 4 actions, and then there are 5 states. Okay. So now the way to decrypt this or how to match this with the math is, let's say you are in state xt. Let's say I'm in state 4. Okay, and now I'm taking control ut to be equal to 0. So I'm in the 4th state. And I'm taking the 0th control, this P should give me a distribution of the next step, right? So that's what we need. Or in other words, from state xt taking control 0, I should have a distribution of over the next step. So whatever my xt plus 1 should be a distribution. What it looks like is like this, okay? So if I'm in state 4 and I'm taking action 0, then this is my probability of transition into my next. This should be 0, pardon me, but now this is what it's going to look like. Meaning, if you look at this, you can say you being in state 3 is very highly probable, followed by 2, 4, 5, and 1. So if you are in state 4 and you take action 3, this is what the probability of your transition is going to be. Do note that it's a distribution, meaning just because it's highly probable, that's not going to be the only outcome. It just means one time I do this, I'll end up in probably most likely in 3, and then the second most likely in 4, and then in. That's what the transition dynamics looks like. Okay, some definitions. This is probably the hardest part before you see the result, right? Not hard, but abstract. So we need to know two terms, a policy, but for the purpose of this lecture, think about it as your controller. All it is a controller, right? But to define it a little bit formally, it's just a probability distribution over control from a state and time. Okay. So in a given state and time, what are the probability over my control, right? And some more definitions. I think you can just look at the equation to be clear. So we call a policy pi stationary if it's only dependent on, it's not dependent on time, right? So you see the input to the policy doesn't have time explicitly, then we call it stationary. If it has time as a function, or as a time as an input, right? It explicitly depends on time, like here, then we call it a non-stationary, right? It's straightforward. If the policy only depends on my current state, it's Markovian. If it depends on history or whatever, it's non-Markovian. Okay. Again, these are definitions for completeness. I don't expect you to, get the intuition behind these, but these are just for definitions. And then there is this notion of value function. It's exactly where we'll see the dynamic programming in action, right? Or in other words, the value function is just going to say what is the expected return, what is the sum of cost. If I start from a state and then follow your controller, let's say you give me some controller and I'm going and putting it in the system and I see what the cost it's incurring, that exactly is what the value function is going to give you. Here, I've consciously left any plots or definitions because that will get me into trouble, right? There are too many moving things. For now, just stick with the definition and we'll see it in action. One side note would be, note that both the policy and state are functions depending on state, right? So the input to them is always going to be state or something or whatever, but the policy will have an output of a vector because the distribution of your control, and the value function is just going to throw some value, okay? It's just going to tell you how good or bad specific state is for the given policy. Yeah.
So is it correct to assume like the value function is like a score? Like how is good or bad, sort of?
So how will you differentiate between score and cost?
Like the inverse, sort of. Like where a good score is like a higher value, sort of.
So my question is, let's say if I have cost like L, if you saw in the integral, right, or reward or whatever, that's for one step, meaning you are in this current state right now, this is the reward or cost that you get. What I'm not following what you mean as a score. Is it like a single step or like multiple steps or whatever, right? It depends on your definition, right? Nonetheless, yeah, it's a notion of how good or bad the current state is if I follow these controllers, right? In the sense, it's not telling one step. One step is just the cost, right? If you're in state xt, you get LT. But value function says, if you're in this current state and you follow the controller forever, how good or bad it is. So in a way, it's forecasting the future, right? It's going to tell you how optimal it is to use this controller in the future. I know it's too abstract, but
So the output of the value function is sort of like, it would be the net cost for everything.
yes,
sort of.
yes, but from the current state. So if I throw any state at you, it's just going to tell you, hey, forever in the future, this is what it's going to look like. Use the control.
What do you mean by distribution of controls exactly?
Good question. Okay, that's right. Okay. So if you think about any controllers that you've seen by far, it's a function. So it takes in an input and then gives an output ut, right? So if you give the input, there is going to be output, it's going to be a function, it's one-to-one and everything. This is totally fine for deterministic settings. But now we are in the stochastic settings, meaning, let's say in certain state xt, the dynamics is going to throw me into a set of trajectory, right? All that is different now is from a notation point of view, it looks something like this. I'll sketch it, just give me a minute, okay? This is what I mean by a distribution of control over state, but let me sketch it. So this pi is going to be something like this, which is just the probability of a certain action. So if you give me xt, you are in state xt, okay? This pi is going to look something like this. Okay, where this is control, let's call it U1, U2, U3, U4. It's very intuitive to see that if the dynamics is stochastic, probably my controller should also be stochastic, meaning I should like sample actions in order to be optimal in that, right? So that's the most general settings. If you think about deterministic, it just says, okay, if you're an xt, this is the only action. Or in other words, in a deterministic setting, the probability for all of it will be 0, but one action will be high, like U4, for example.
since we're talking about the 3 time steps, so is this a control for the next time step, or is this a control for the rest of
The control is for, it's just so it's a mathematical trick they play all the time. You can swap it a little bit, but to be more precise, yes. So let's say I'm in xt, I apply ut, that's the action current time. It throws me to xt plus 1.
Okay, so it's not, when you're saying follow the control, then it just means follow to the next step.
Yes,
not
so it's
necessarily
one step. And then once you go to the next state, you'll once again call the controller and say, hey, what is my new action?
Right.
What is the new controller that I need? New controller. Okay.
Could you clarify what you mean by policy being vector value function and value being scalar value function?
Cool, great question. Right. So think about this. So here, if I put an xt, okay, this notation, I don't know whether you're familiar with it, but nonetheless, if I throw in xt, which is like a point or whatever, what is the output of this policy pi that I've sketched here? It should throw out the probability over all the actions, right? So let's say the probability of this was 0.1, 0.2, 0.1 again, and whatever is the remaining, since it should be what 0.1 plus 0.2 plus 0.6. Okay, so the output of this policy pi is going to be a vector of these probabilities. So for the first action, it was 0.1, 0.2, 0.1, 0.6. Does this make sense? So the pi is technically the output of pi. If you give a certain xt, it's going to be this. And then you do some sampling from it. So since it's a probability distribution, you sample from it, and then you get your action. Most likely, it's going to be this action, because that has the highest probability. But this is the vector I'm talking about. It's a vector of probabilities.
Okay.
Does that make sense?
Yeah.
Okay, good.
How are those numbers actually repeated?
We'll see, Let's narrow it. Okay. Any more questions? Oh. I didn't expect this much questions from this specific slide. You guys are following. It's good. Okay. So here is the problem all put in one shot. And then the next slide will be the solution. Trust me, I'm not, lying. It will be the next slide. Okay. So this is just for completion, right? So we are interested in solving this problem. There's a new word called finite horizon. All that means is this integral is over some finite t, capital T. Okay. Or visually it looks something like this. Okay. So this is the state, 4 states are there. And then there is a finite time interval, 1 to t. All I'm saying is this is like you can count them. It's not like going on and on for infinity. Okay. So now you have some stage cost, which is at some state xt. If you are in state xt at time t, this is how the reward is going to look like. So let's say this LT is exactly defined this way. So if I am in state, let's say 2 at time t equal to 0, this is exactly the reward you're going to get. The value of whatever is in this grid is the reward you're going to get. Similarly, if you are in state 3, but in time 3, this is the reward you're going to get, right? It's just the definition of reward or cost function, however you want to call it. Okay. Now, here's my question to you guys. Let's say I randomly pick a time, that is the third step, and then I put you in state 2. And now my question is, what is the optimal thing for you to do? So I've given you a reward function. I want you to maximize this. I put you in this state in this time. How will you even think about solving this problem? Or what is the optimal control for me? Such that from that time and that state, forever I have the highest cost, or sorry, lowest cost, or I'm optimal, right? So how do I choose a controller from this state and this time such that this is maximum? A very non-trivial question to ask. But one detail that was missing per se is that it is subject to dynamics, meaning it's not like a random sequence of x fields. It's not some mathematical sequence. It follows this exact transition dynamics. It's totally fine if it makes you uneasy. You're not fully grasping it, right? Well, you can. It's just a as I said, an initial point for you to tinker with. Okay. So here is the algorithm. So this is the problem we are setting to solve, right? I don't have a good solution. Does anybody want to take a attempt at a solution? So when I was first asked with this question, I said, let's say I am in 3 and I am in 2, I will choose the action. So let's say I am in 3 and I'm in state 3, right? And this is my next time step. I'll probably choose the one with the maximum reward. Okay, so here purple means higher, right? I should have put a color bar, I'm sorry. So let's say I go to purple, right? So higher reward or lower cost or whatever. That's the immediate action such that I will maximize or I'll optimize the cost. So I say I'll go there. Right? And then my professor said, yeah, you're greedy. That's why you do that. Right? I'm not even making this up. It's an actual term, right? Because you see, at this time and this state, I only thought about my immediate returns. Okay. But the optimal control problem is not that. It wants you to be optimal, or it should maximize or optimize this forever in the future, or until capital T. right? So don't be greedy in life. That's what I would like to say. But then Bellman gave it to you as an algorithm, right? Non-greediness as an algorithm. So the actual term is dynamic programming, and it's called backward recursive value iteration. Quite a mouthful, but it's just 3 lines. You implement these 3 lines, you can do it in your sleep. You know, it's MATLAB, you just make 3 tables, it's gonna work. And let's see how it does that. Backward recursive, meaning when we try to solve the problem, we don't start from time step 0, we start from the final time step. Okay. Or in other words, you see, we initialize this value function v of xk, having k equal to capital T, right? So the last time step. And then I say at the final time step, there is no future there, because if it's the last time step, already it's over, right? So I just initialize it to my per step cost, because there is no next step, there is no next reward. Okay, so I initialize. Then I just solve this, or I just compute this one weird yet simple looking equation. Okay, I'll tell you why it's simple, right? And then I do this for enough number of times. So let's say I do this, I'll explain it in a minute. But if I do this, then I go to step back, and then I change k from k to k minus 1. That is from capital T, I'm going to capital T minus 1, and until 0, you're done, right? So this looks very math heavy, but it's just a for loop, right? You have k iterations, and then you're doing a couple of computations, and then you have and then once you're done at t equals 0, you're done. You come out, right? Or in other words, you have computed something. Okay. So this is why I'll explain how the principle of optimality and everything comes in. But that's why it's an algorithm, right? It's a for loop. You can implement it in your computer right now. Okay. Let's recollect the principle of optimality. It said the optimal objective value from step k is your optimal value from the stage reward at k, and then the optimal objective for k plus 1 step, right? So, or in other words, if I am optimal up until time k, I should also be optimal from k plus 1 time. The exact principle of optimality. And this is how you write it in math. Okay. So what we want is at time step k, at state x, we want the optimal value. We want to be optimal, right? That means I need to minimize this thing, right? Which is my stage reward, it's my current reward, and my expected value forever in the future, or my expected value from k plus 1. Okay. Let me repeat. So the optimal value at time step k is choosing whichever action u that minimizes my current stage reward and the optimal value forever in the future, right? For k plus 1. Okay. This is Bellman's exactly Bellman's principle applied in equations. Don't worry about getting the exact math right, or you should really tinker with it to understand what's happening, right? But I'm just trying to say that the principle is intact. But see, one thing really beautiful happened there. When I showed you all the problem in its at most scary way, we were searching for functions, we were searching for pi and whatnot. But see what it became. Now we are just searching for a single step u, right? So instead of searching for a function, we are just searching for a single control. That's what it became. And all thanks to the application of Bellman's optimality. Okay, you run this, you get a value function. That's good. But all we cared about, this is a control course, we want a controller, right? We want a controller. We don't want a value function. What are we going to do with a value function? Then the controller is just says whichever action u, so in the current state or in the state x, whichever action minimizes this term, that's your optimal control. That's what Bellman's value iteration tells us, right? So if you want to know whatever is optimal at time step k from state x, just compute this. Okay, that's the algorithm. And I think you guys survived it. Now it's time to look at some good code, right? But any questions on the algorithm, shoot now.
Yeah, so sorry, what's the difference between the last line, your higher policy function versus the value function that you labeled as 2?
You tell me, it's looking at you right there. What's the difference? Yeah, let's look at it from there, right? Same. Yeah. The expected value, dk, same thing, nothing different. LK, okay, LXK. When you come here, that's good. Okay, this is minimum, this is argument. Minimization means it's the minimum value that this is going to take. So choose a control u. And I'm not interested in what the value of u is. I'm just interested in the minimum value of this bracket, whatever is inside this bracket. But here it is saying I'm interested in the u that minimizes the value. Right? So it's the argument versus the value itself. Okay, or let me just, where's the marker? Okay. So let's say there's a function y equal to fx. Okay. Now, if I'm saying I want to minimize f of x subject to x, right? Then this is going to be y star, or in other words, the minimum value y is going to take. But at the same time, if I say argument over x, then that's going to be x star. Or in other words, what is the value of x for which f was given? Right. So this will give you the control. That will give you whatever the value is. Yeah.
Where do the constraints and the dynamics stuff?
Very good question. You got me. You got me, Bellman, and all are scam. There is no constraints. We can't solve constraints. Or in other words, in the stochastic settings, the constrained optimization is still an unsolved open research problem. Let me know if you solve it. Yeah. Oh, yeah.
So when you say the optimal value at table source, why is it the expected? Is it? I'm confused as to why the optimal value is the expected value of the value function.
Good, good, good. Not that I enjoy your confusion, but good. So you're in state xt, and you're applying u. But it's a stochastic dynamic. What does it mean? You're not going to have a single xt. You're going to have a bunch of x's. So what this says is, over all those xt's, whatever is the average of this value function.
Oh, and that's back to your cost function.
So I'm struggling to figure out how you know your state at like going back through that for loop. Like, where does that come from?
Good question, good question. Where it comes from? So that's kind of the downfall of Bellman as well. I'm so happy Bellman is not taking this class. I'm really sad. You guys are picking up all the problems. So this you need to compute for every state explicitly. Or in other words, let's say starting from the last time step, and let's say there are 4 states. For each state, I have to explicitly go and compute this equation, and I need to put it in table. Meaning, it's not that an x is coming or it's coming from some state estimator or whatever. To compute this problem, I need to go to each and every state, do this math, and I need to save the line. Does that answer your question? Or where it comes from?
Don't we get a value function or something that's minimized over that? And then how do we? Isn't that like a scalar value that we get now from this function?
Yes.
And so how does that scalar value tell us which state we were at before?
It doesn't, because you see the loop is initialized at k equal to t, and then you're going backward in time, right?
Yeah.
So with each time, let's say for each state, maybe I should write down this. For each state, we do this computation.
Okay.
Right. So what I'm trying to say is, so let's say you're starting at the last time step, and there are 4 states. So for each state, you initialize this value.
Yes.
Okay. Yeah. And then you come here, and then for each state at step k, which is t minus 1, right?
Yeah.
You compute it over all the states.
Yeah.
Right. So I think it will be once again better.
Now we give us a control input though, a u, right? And so do we have to like use that u to figure out what our state was before?
Not necessarily, because that is where, oh, okay. I now see your confusion.
Yeah.
When you compute this expectation, I still now didn't tell you how to compute this expectation.
Yeah.
When I open this is the exact map you're computing. What is it?
Probably
The dynamics.
Oh,
The transition dynamics, right? So when you compute this value function, or the expectation of the value function, you are implicitly accounting for the dynamics. It already tells you what are all the states you're going to do. So the right way to read this expectation is, so let's say you are at time step xt, you're applying control u, and then there is some probability that you will reach xt plus 1, and that's this specific. So there's a probability that you reach xt plus 1, right? So what we are saying is the value for the next step is multiplied by that specific probability. So that tells you where you will land, right? I know it's still confused, but I think the code will make it clear.
okay.
So let's say state 1, state 2, state 3, and then this is at time step t. And I go to t minus 1, still state 1, state 2, state 3, state 4, pick a state, we are in this state. So now this p is going to tell you what is the probability for each transition. And we average over all of it.
Yeah, I understand.
And then we go to t minus 2, same thing. So we do this for all the steps. So let's say we go to S3, we do the same.
Okay, yeah, I see.
Right? That's what made Bellman scream one day at night, curse of dimensionality. Right? Because you see, if you have more states, let's say here it's 4, you do this math for every time, for everything.
So it's just computation is
Exactly.
impossible.
Yeah, good that he was a mathematician, not a algorithm. So computer.
I have a quiz.
Yeah.
Where do we get the
Where do we get what?
P, the state.
Oh.
And this probability if you don't
Weighted
apply-
part, right? So the assumption is stochastic optimal control. See, that's why I'm still calling it optimal control. There is a model. Somebody has to give you the, right? So if you give me P, I can give you control. But if you don't know what P is, that's what the part 2 of the lecture is for. Okay. Okay, let's do some code and probably take a quick break, but all good questions. I'm sorry, this has to be in Python because you need to speak the language of learning. That's what the cool kids are doing these days. But also more importantly, I suck at MATLAB. I tried writing this code, but it didn't work out. But it's going to be simple. We're going to take it step by step, right? Exactly the philosophy of Bellman, step by step. Don't think about the entire problem, thinking about searching for function, but think about computing the one step. Yeah. So the capital T from the problem before, I'm thinking about 5 steps in the future. I kind of glimpse this through, right? This is for you guys to read at your own pace, understand, and then see how it's transcribed. But for the purpose of this demo, all we care about is, that somebody gave you a P and L and all the other parameters. We are interested in just this one, okay? So T, the number of time steps. We want to think about a finite horizon problem that is 5 steps long, okay? And then the number of states were 4, much like the example that I talked about, x is equal to 4. So by the way, here is a slight abuse of notation. What I mean by x is equal to 4 is there are 4 states. Okay? And then the number of states is equal to the number of control. This is purely a choice for this specific problem. If you read the English, you'll get the math, right? But it doesn't matter. It can be arbitrary. It can be 3, 2, whatever. And then I said the reward function, or in the optimal control literature, this is the cost function. So you remember the plot that I did where I said you're in a specific time and in a specific state. Here is your step reward. This is that function. So this is just a 2D array, right? Where if you see there is 1, 2, 3, 4 rows, and then there are I think 4 columns, right? So technically I did a mistake where this should have been okay. I think it's fine. So this reward just says that if you are in time step X and you are taking an action U, this is the reward you're going to get. So if I go to row 2, then I'm in state 2, and I'm taking like action 1 or something, I get a reward of minus something like that. Okay. And then you have the state transition dynamics. I'm sorry again, but I'm just initializing this. Again, for the purpose of this, this is given to you, right? Whatever I explained to you assumes all these are given to you. It's not important, right? So there is some transition matrix that's given. And here is what Bellman gave us. Okay. So we initialize policy and value. So this is where the name tabular comes from, because both the policy and value are nothing but 2D arrays or whatever, right? So they are tables, and we start from 0. Okay, we set it at 0. And note that the dimensions of the policy are x and t minus 1, meaning the number of states. And then this is just t minus 1. Anyone tell why it's t minus 1? And not t, because I would expect, okay, you are for every time step x, you need to know what the, at time step k, that's the optimal policy or whatever, right? But it's t minus 1. The reason is once you're going to the t minus 1 step, there is no control after that. When you're in the final state, there is no need for a control, right? So you only need t minus 1 columns, so to speak. And then here is the value function. It also has zeros, and then it's of this specific dimension. And here we initialize the terminal cost or the final reward, right? And then we do the backward recursive upgrades. Okay. So for k in this step, this is the backward step. So we start from t minus 1. We go to we start from t, we should go to t minus 1, t minus 2, t minus 3, all the way till 0. And for each state x, that's what this question was. For each state x, we compute this equation. This is exactly the expectation that you saw. See, it's very simple by means of 2024's computation. The reward plus a product of a matrix with a vector. That's all, right? And then the value is nothing but the min. The policy, the optimal policy is the argument. That's all. So this for loop will end because there is a terminal time step, and then there are finite number of steps, which means in finite number of iterations, you're gonna escape this. So the good thing about all this is, this link is there in the PDF, and Google is kind enough to let us run this for free. So you don't have to install anything in Python or anything. Just do this. Just press connect and probably go drink some water or something. Take a break. Yes, we're connected. We've got RAM, everything. Okay. Python is installed already. You don't have to worry about it. Much like how you do in MATLAB, you're just pressing play. There you go. Yeah. So for this specific P, R, L, X, whatever, here is your optimal policy. Here is your value function, right? So what this value function is saying is, if I'm in state X and I am in some time step T, this is the value. But you see, I said this should be a vector, right? But it's not exactly a vector. I'll explain this in a minute. But you see, this is weird because this policy or the policy, whatever the policy is trying to say is if you're state X and then you're in time step T, 3 is the optimal action you should take. That's what it's saying. Yeah. So if I were just to visualize, it looks exactly like what we did before, right? So this is going to be the optimal policy. This is going to be the optimal values function. So the policy at any given state, let's say 0, at time 0, it's saying that the optimal action is 3. Okay. I think it was your question, why it's a vector, right? But here it's not a vector, right? It's still it's same plot, scalar, right? Why? That's that element, right? But that's the code. I'm going to stop it here because you guys can tinker with it. That's the best way to understand and go about it. But that's all that you need to know. So quick summary of what happened in part 1, and then we can take like a quick break. So the finite horizon case, right? I gave you an algorithm. You saw it in code, and there is a theorem, very nice too, right? It says a Markov policy pi is optimal if and only. That's the important part. It's a supervisor of value optimization algorithm. What I'm saying is, let's say you're not using my algorithm. You came up with your own algorithm and you found the optimal policy. Still, it should satisfy my condition, right? Or in other words, an optimal policy implies an optimal value function from this algorithm, or an optimal value function implies that it is corresponds to the optimal policy. It works both ways. So it's a sufficient and necessary condition for optimality, a very powerful result, right? And what it is intuitively doing, you can forget all the theorem, that's not for us. What it's doing is it's cleverly exploiting the temporal structure. You see, instead of thinking about a function, think about one step at a time, because the structure is likewise, right? And it's solving, instead of finding an infinite dimensional function, it's solving it one step at a time. Okay, find the control at one step. It proves existence, gives an algorithm in finite space, not a big deal, right? But you see, this is the exact point that I would like to follow up on this answer. Solution to this stochastic optimal control is a deterministic Markovian policy. Meaning, though we initially thought, right, to be more general, that it should be a vector, it should be probabilistic and whatever, what Bellman eventually found out was this specific setting, you are totally fine with the deterministic policy. Meaning, there exists a deterministic Markovian policy, which is optimal. You don't have to search through all these weird function classes, which is outputting, probabilities, vectors, whatnot. Just search through the subclass of problems, you got yourself a function. So that's why that was still 2D, it was not 3D. I'm going to leave you with that. Once you take care with it, once you realize it, let me know if there are questions, right? But it's very interesting. But the key ingredients for this to work is threefold: Markovian dynamics, additive cost, in expectation. Even if one of them are not present, then none of this beautiful result exists no more. Okay, and the proof is so straightforward. Even if you read it today, you'll understand it's just mathematical induction. Okay, it just is super straightforward. And note that the principle generalizes to continuous space, meaning if I take X to be continuous, U to be continuous, the principle is still valid. Unfortunately, the algorithm is so. You cannot just compute the control like this, but the principle is still valid. Okay. So with that, let's take a 5-minute break and let's resume to part 2, which is reinforcement learning.
Earlier in the slide, I can play the customer response also. I just didn't understand why what in the sense of the recursive method would that kind of accomplish compared to what we can like not it makes me like you start with the what if you start the other way? Like what's wrong with going that way?
So you see, the reason it's starting from the so this is a boundary value problem. Familiar with meaning it's like you think about the dynamics. What is just talking about dynamics, like dynamic systems equation, right? So you need either the initial condition or the final condition to solve it. So in the finite setting, you need to start from the back because T is finite, meaning there is a last state, right? So we do that. But you are right in the sense that think about an infinite horizon. Meaning capital T is not even finite enough. So
So I feel like you have to go all the way back and you have to calculate all the possibilities.
yeah.
If we go forward, doesn't that also be like the same?
It's mathematically they are exactly the same, but you see, capital T is finite, we can start with. But imagine you LQR, Professor. LQR is infinite, T is infinite. How can I start from behind? You can't, right? So in that setting, it is an infinite horizon setting. We start from the front. That leads to a different algorithm called the forward forward recurrence, right? So probably after class, I don't think I can give you the exact. Guys, slight trick, time scaling trick, and then we do the forward recurrence. But they're exactly. I mean, computationally, you're not going to be 1/n. Both are exact things. But in the infinite horizon setting, it's not even possible to do that. You can only do forward.
Difference.
Yeah, so now we can start in the sense that using penetration goes at 6.2. So that was for the infinite horizon setting, where forward regression is what was used. What Bellman said is if it's infinite horizon, then I cannot do this backwards. Only with forward regression. And there is
Like I can do change whatever I want.
I'll give you some notes. Okay, but you're totally fine. I do it.
No. Basically, I'm gonna hack these things, bro.
At the
class. At the class.
Yeah.
Dude, it's another year when you're school. Function or your control. That's how the military works. Yeah. Function.
So what is the solution for this problem?
I don't know, it's so extra, like what?
I want to answer.
Yeah.
That's what I mean by solution. Of course, I'm playing loose here. But what I'm trying to say with that point is, you see this. Ideally, if it had been a vector and water, this should have been a probability distribution.
I think it's cyber is like, hey,
But you see, you give me X and
that has to do with like.
why is it equal? It should have been.
You can get.
If I had been a stochastic policy, it should have been a distribution.
They
But
say
I
that.
logic says, no. You're an X and K. I can exactly tell you the unit optimum.
Yeah, it's very.
In other words, if you take a deterministic function. Okay. So that's what I mean by deterministic. And the Markov is because you see
That's why you're
like 5 weeks or something.
Yeah, I heard it's because cyber's like.
That's one of the reasons, but I said the combination of the three is what leads to this. Meaning, even if you have Markov in dynamics, and you remove
Yeah, so
the
like always I feel like
there is no need for the policy to be
The
Markov.
problem is every update is like
Right?
another.
But my point
$2,000 or
is, let's
something.
say you give X and K.
So
So
it's
that
like,
time
hey,
say all
so
you need
pay
to
for it.
compute is just X
It's
and
like
X and K.
ideal goal
So
for
it's
like
X.
cyber.
Then you should in K, if you exactly tells you then you are you get the deterministic function.
You have to constantly get educated. It's like constantly listening to podcasts.
Would you?
Jealous. One dude I know who's making your. He's a cyber. Yeah, but he's like one of those child geniuses that was picked up. He's like, oh yeah, I think you can do part-time job. But I'm going to do it." You know what our brother do?
What?
He does Wikipedia level of searching information, pushes it out, and that's it. He doesn't even hack anymore, he just says, hey, yo, this is happening in Israel right now. That's it. Joe, who's being that bad? What's
What's you missed on the best part. Okay, this is a very personal lady. She does all of them. Hi.
What do you got?
5% on either usually.
And then I can tell you about how. Yeah, like what do you what do you need to, what is ideal for presenting?
I guess that's why you think
Focus on the system. Because if you look at the purchase order.
Okay,
Like
we begin.
Everybody emphasizes on it. I have some RT1 or two. One station, some very powerful chemicals in my sleep.
What you guys are doing? Three years to get to bike.
Haven't started.
Sometimes standing is very hard. Because think about walking, feeling dynamics. Right? You can just do this, keep stepping. Standing needs like absolute stability, right? I work with RL, as you know. It was very easy for me to make it walk or walk because the controller is like it's not always perfect. Standing, my controller is like standing. Yeah. Yeah. So there is this one guy named Mark, right? This Google, right? It's called Rainbow Hopper. Back in 80s, when the average compute is fraction of what your phone has right now, he was able to make these hoppers backseat and like hop. Yeah, the guy with the blue shirt, right? So he was able to do all that. But you go to him, you tell him, hey, make your hopper stand. Right? So he came up with these three heuristics, very good. I think you guys know some using Tribert heuristic for your food placement.
Yeah, I guess he has something.
He's the guy. He's the guy. Okay. Let's start the reinforcement learning side of things, what I promised, but I, didn't deliver the first part. So to come out clean, when I first was seeing all this hype, that's going on, AlphaGo, ChatGPT, whatnot, I was this naive sophomore who thought, intelligence is solved, reinforcement learning is the key. And then I went, so it was like a really, really fast, amazing car, race car, right? And then I went to try to understand this. So I opened the hood of the car. Why was I confused? Or in other words, whatever is going to happen in reinforcement learning moving forward, it's going to be a very thin line between a heuristic and a theorem. Yeah. You see, don't confuse it with what Bellman gave us. Bellman gave us something that is so simple, almost like a heuristic, but it has all the rigor of a formal theorem. But reinforcement learning is not going to give us that. Yeah. So when I first tried to learn this or understand what's happening, I was very confused because somebody does something and you ask him or her why they did it, because it worked, and then they don't talk more than that. Okay, it's really unsatisfactory. Yeah. So that's why I thought, even though it was math heavy or whatever, right, I introduced you to the DP, dynamic programming perspective, right? Because that's what lets me sleep peacefully at night, right? Because I know, okay, there's some supporting theory. Eventually, somebody will figure it out. But at this time, is when this so-called reinforcement learning was, emerging. Let's open this one. Reinforcement learning, 2 words. What is learning, right? So you may have seen different aspects of it: supervised learning, unsupervised learning, something learning, right? All that means is we don't expect or we don't assume some prior model or something is given to us. All we assume is that there is some data or an ability to collect data or to collect experience, okay, so to speak. From this experience, I would like to infer whatever that I want. That's the key. All I assume is there is some data given to me, and I want to infer maybe an optimal policy, maybe a function, maybe an approximate, whatever it is. But all I assume is the availability of data and not some model, not some structure, nothing of that sort. That explains the learning part of this name. But what about reinforcement? What does it mean? Anybody?
You do good things, do bad, do like carry on doing the good things. If you do bad things, don't do them, sort of.
Yeah, we're not advising, but yeah, it's more like, think about your grading of your homeworks. Okay, you did homework 1, gave it to your grader. He or she graded something, gave you back a score. Your turn, not mine. Score, right? A reward, right? That's all it is. It's a reinforcement. So you did good. I'm assuming you did. You got a positive, good reward, right? If not, you got a negative reward. Okay. So the notion of reinforcement is just that, whether you're giving a feedback of how good or bad you're doing. It's not about whether to do good or whether to do bad. It's just about giving a feedback. That's it. So now when you put these words together, all this means is, hey, I'm ready to give you some feedback of good or bad, but I want you to learn the rest. From this singular scalar feedback, I want you to learn everything that remains. Yeah. So before we actually see or dwell into these magical methods, so we need to meet the man behind methods. So for Bellman, I said man behind the math, but for him, I'm using methods, right? So he is a professor at computer science. His name is Rich Sutton. Okay, he was the one who formalized reinforcement learning. So before that, it was a bunch of psychologists, a bunch of neuroscience people sitting together, smoking their whatever they smoke, and then they're trying to say, hey, this is what the brain is doing. You know, there is trial and error. There is like interaction. And then they were happy with their own theories, and they were doing this stuff. But he was the first one to say, okay, that's something, but let's not be this cult. Let's try to actually make it formal. Okay, he took an attempt there. And the word here is computational reinforcement. What does the word computational mean here? It means he took these psychological backgrounds and he put some algorithmic aspects to it. Meaning you can use this and you can actually solve some problems. Right? So a couple of algorithms under his name is TD learning, Dynam, etc. We'll see a couple of them today. But here is the philosophy, or here is kind of the point, is what the difference of reinforcement learning to dynamic programming is going to be. Is this singular philosophy? He says, approximate the solution, not the problem. Yeah? It's not very evident what he's trying to say. With all his beard and everything, he looks like a wise man. This should mean something. What he's trying to say is, if you think about your MPC, you saw Hector, right? Hector has legs. But when you wrote your MPC, you said Hector is legless, right? You said it's a floating potato in space and I can apply forces. How is that valid? Is it valid? No, it's not valid. There are legs, man. There are legs. Hector will be very often there. It has legs. But that is a good enough abstraction for you. Or in other words, you were able to simplify the problem. You were allowed to simplify the problem. And that's totally fine because all you cared about was walking. Whether you're walking, you're fine. Doesn't matter whether my math knows that I have legs or not. As long as I'm walking, I'm happy. You were given the freedom of choosing that abstraction. And that optimal control is happy with. Okay, I assume a model, and as long as I design an optimal control, I'm good with it. But it's exactly what this guy is against us, the law. He says, don't approximate the problem, right? You should not approximate the problem, meaning you should try to come up with a controller for Hector with its legs, non-linearity, everything. But what he is okay with is approximating the solution. Meaning, what he's trying to say is, it's okay if I'm not tracking the velocity at 0.1%, 0.2% error. It's okay. But as long as if you're able to find a solution for the complete problem in its entirety, that's all we care about. No special cases. Okay, so that's what he's trying to say when he says approximate the solution, not the problem. And that's exactly the philosophy of reinforcement learning. What we'd like to keep on for moving forward. Reinforcement learning. Okay, so I think a couple of you guys were super smart to bring this up already. Okay, but that's the downfall or the limitations of DP, these two words. Curse of dimensionality, meaning if the number of states and control and time, whatnot, if their number is increasing, then the computation becomes to an extent impossible. You don't know how to handle that. Second is it assumes the transition dynamics is given. I don't know, one of you brought this up. Somebody asked me who gave the model, right? I would have said God. That's a different argument. But nonetheless, we don't know whether who gives you the transition dynamics, right? So that's exactly why we need learning. Here is a heavily, I would say, overhyped figure, but I think it does justice to the principle. So now let's assume that there is an environment, or this is just a fancy, light word for the transition dynamics. This is your transition dynamics. But you see, my policy or the agent doesn't assume knowledge of the transition dynamics. Meaning, I know that the transition dynamics exists, but I don't know what that is. And the only way that I'm going to interact is through the signal. Okay? Or in other words, your environment tells you that you are in gives you some observation state. You see, it's not even state, it can also be observation. Some feedback of where you are, or some feedback of your state, and some reward. Moving forward, we are going to be all very optimistic. Okay, so we are going to use rewards instead of cost, because if it's cost, we are minimizing. Very pessimistic. Let's be optimistic, so we are maximizing our reward. Yeah. So you get two signals. One is the feedback of the state, and then the rewards. Yeah. And then your agent is allowed to take an action U, and this cycle. Meaning the agent has no knowledge of the environment or what the transition model is of the environment. It just has access to the signal. Now the RL problem says is come up with your learning, beautiful, amazing learning algorithm that can maximize your returns. Okay, learn to maximize the expected returns through trial and error, or in other words, it's sequential decision-making problem. Meaning, I'm not interested in maximizing the single RT, or in other words, I don't want to be greedy. I want to say if I do this iterative forever, I want the agent to act such that the returns is maximized. So forever, I have the highest rewards. That's the goal of reinforcement learning. Okay, but without the assumption of the transition dynamics. We don't know P anymore. We only have access to these signals. This brings up a very interesting problem. Or this is what keeps people like me in business. Yeah. What is that? See, when the model is given, it's safe to say everything about the problem is known to you, right? Albeit it's deterministic, stochastic, whatever. But if a model is given, almost everything is known, right? You start at time t, you do some actions, you see where your trajectory leads, choose the optimal action, or in other words, do expectation, all the math that I showed you. But the moment you remove the access of the model, all bets are off. This brings a twofold challenge or a dual objective. So unlike your previous optimal controller that Bellman gave us, RL has a dual objective or two problems to solve. So one which we are familiar with is exploitation, or in other words, we just want to act optimally forever. But since now we don't have access to the model, there is a dual problem called exploration. Okay, what they mean is you need to collect useful data first, right? First, somehow, let's imagine this agent I put in this environment. I need data that is good enough for me to learn from. So it's about data collection. And using that data, I would like to improve performance. So the second one is something we already saw in optimal control. That's what we're doing. But now there is this new problem of exploration. How to collect good data. So for the people who are not familiar with these terms, I've always seen things like this viewed in control literature. So if you're interested, there is something called as dual control theory, right? People in the 60s were breaking their head about this, classical control theory. But this is the fancy new term in the learning domain, exploration versus exploitation. These guys will come in a bit, but this is the dual problem. So now it's like a dual-edged sword, right? Because if you are exploiting with just the amount of data you have, right, then your solution is local to the data you have. So let's say I have 5 samples, and then I pick the optimal action. It's optimal only with respect to 5. But what if new data pours in? I have 10 samples. Then the new optimal will be something else, right? So unless and until I have enough good samples, 10, 15, 20, I don't know. You cannot even talk about having the optimal policy, right? So that's the dual problem there. You need to collect useful data. You should also use the data to improve performance. Harder to do than harder to say. It's easy to say than what this means, it's a very simple yet ambitious problem. You see, anybody could understand. There is agent, environment, you interact, get rewards, maximize it, go home, sleep. Very simple, right? Like to me, reinforcement learning was very accessible because I understood the problem really immediately. That's the problem statement. There is no theorem, there is no regularization conditions, there is no equation, just a block diagram. You understand it. But then it's ambitious, right? And what these learning people are always interested in is, can a single algorithm learn any problem, right? Or there is this one thing called reward hypothesis. What it says is, let's think about any subjective task you want. Let's say, getting up, coming to the school, let's say completing your homework, or let's say, improving in your career, whatever task it is, as subjective, as abstract, as high level as possible. The reward hypothesis says any such task could be transcribed in this format, meaning there is an environment and you can always find a reward that tells you that, this is the good thing to do for the task. So what these people are in search for is an algorithm that solves any problem, right? There is a trade-off for this. So this was not the perspective of optimal control. Optimal control things are very clear. You have one robot, you have one system, that's all you care about. But here these people want generality. Or in other words, they want one algorithm to solve everything rather than specific performance. Meaning, they want to find an algorithm that works for a biped, a quadruped, a manipulator, a drone. They don't care. They don't want to differentiate. They don't want to discriminate. But if you now compare for a specific task, a specific controller, they're not cared about a very good performance in that one system, right? So what I would call this as is the learnability problem. can we even learn an arbitrary task? So that is why often they are happy with a solution than the rigorous optimal solution like we saw. This problem is hard in its own right. So, that's why this all this is valid. Any questions on just setting it up on the side until now? It's clear? Yeah, that's what I thought. Okay, so I said that's the problem, and this started around in 2000. And people said, oh, there is this one block called R algorithm. Take it, put your problem, things are solved. World peace, just throw it in, R will solve it for you, right? But boy, were they wrong. Yeah, meaning, even though they set out to find this holy grail of algorithm, they couldn't. What ended up happening is there were this full taxonomy of algorithms, right? All of them are general enough, meaning each of them will solve like some handful of problems, but none of them will solve everything. None of them is able to solve everything, right? So they ended up differentiating into two, and then there were subclasses, or in other words, each variant would solve specific set of problems, but we don't have like that one algorithmic or a single holy grail of algorithms. Okay, so I will not go through, we don't have enough time to go through all of it. We'll see some of them today. But you see at a high level, the R algorithm can be split into two. One is called model free R, which is what we'll be doing for most of the time today, where you don't care about anything in between. You don't care about any structure, anything in between. Can I directly learn to control? Whatever that means, I'll explain in a bit. And on the other hand, there is the alternative that we can do is something like what an MPC does. It's like, let's say I learn the model, and then I call an MPC. That's an equally valid idea, right? Because you say you don't have a model, that's the real. Here is some data, learn the model, and then use that to do your control, like MPC or whatever. Okay? I'll take a minute here. What do you guys think is the better approach, or why do you think one philosophy would be better than the other for learning? Right? I know you guys don't have the background, but just take a shot at it. Like philosophically, intuitively, what does it tell you? Is it easy to learn the controller directly or model and then doing MPC? What do you guys think?
Depends on your goals.
Goals? What do you mean?
So like if you want to control it over sort of broader scenarios, then like maybe the RL is better. But if you kind of have specific like parameters that you're using it over, then maybe your model based might be better.
Okay, so if you know something about the problem, it's easy to do model based.
Yes. Probably learning control directly would be easier because learning models involve learning like the model itself like literally have to learn how to do F equal to MA within itself, or like do differentiation, do integration, all these math operations that might be very difficult to learn.
Right. So maybe let's take a poll, just for the sake of it. You guys don't have to think it. I'm not going to hold you for your answers, but how many of you think this is going to be easy? Raise your hands. 1, 2, 3, 4.
In terms of implementation, it's easier, but in terms of learning, it requires.
You think so? Okay, that's a good answer. Good answer. So I'm assuming the rest are all model-based fans. You want to still lift your hands, no? Is that? Okay. Let's assume they might. This is a big dilemma. Yeah. Now let's for a minute think. What are you guys doing? So let's say, for example, I'm trying to grab this cup right now. Okay. When I was born as a kid, I didn't know how to hold a cup. Now I know, which means I've learned it, right? What did I learn? Did I learn F equal to MA? Did I learn a model and then to hold the cup? Or did I learn to control directly? So I hold the cup. Okay. When I was a kid, I was not. Now I can. So what did I learn? What about the problem did I learn? Okay. So one way I like to think about this is it really depends. Yeah, I think his answer is somewhat close because you see this cup. Okay. And my hand is nothing but F equal to MA. There is soft body, like there are interactions. And the moment I touch it or hold it like this, see there are contact forces everywhere. Okay. If I'm learning F equal to MA for this problem, it's definitely harder, right? Because I need to, my brain should reason about all these contact forces, do a free body diagram, right? And then solve the statics problem, right? I don't know. But even if you close my hands or whatever, even if you put a mask or something, holding just means a binary thing to me. Hand open, hand close. That's it, right? So in some settings, I think learning the controller is directly straightforward. But if there are problems where you have to reason about the future, So think about a problem where I woke up today and I'm planning to go attend, I'm planning my entire day, right? So I wake up, I brush my teeth, okay? And then I decide and I plan my day, and then I need to have a lecture at 11 a.m. and then I have to go have lunch, and then I have to, do X, Y, Z, multiple things. This specific task requires me to predict, right? Whether will there be rain today? If there is rain, what should I do? If it is raining, what should I do? Right? So let's say if there's a time clash. Let's say suddenly today the bus is not going. So these are all aspects of the dynamics. And then I reason about it. I think about it. I try to predict what the future is holding for me. So in tasks like this, I think it's very easy to learn a model. And this model need not be very accurate as an F equal to m. It can be an abstract, discrete model as well. So that's exactly what we are seeing in the algorithm as well. You see, there is no one good answer for all of them. And the reason is it really depends, right? Depending on your task, it's easy to that. Depending on your task, maybe it's better to do that as well. Okay. Okay. So now let's dwell into one algorithm. So specifically in part 2 of this lecture, we are only going to see Q-learning, right? So there are essentially just two ideas, okay, that you need to know to do all of learning in this setting. Or at least this is what people did when they started to think about a learning problem. Okay, so the first is a learning rule, right? So let's say I throw you in some environment, I've given you some data. How do you learn? You need to come up with a rule. So I'm very clear with my terminology. Meaning it's just a rule. You don't have to justify your rule or whatever. It's just a rule. Okay. Oh, okay. Supposed to demonstrate it. Maybe whiteboard is better. So to give you a taste of what such and such learning road should look like, let's start from a problem that you guys all probably know, right? X dot is equal to U. What is this? It's a first order system with some control signal U. That's all it is. It's linear, everything. It's continuous time. That's why it's X dot, right? But now, let's say if I open it up into xt plus 1 minus xt divided by delta, some delta, it's still equal to U. What is this? I just managed to open up the derivative and have like a, finite discrete time step. Yeah, that's all I'm trying to use. Okay, that's it. Now, if I rearrange the little bit, I'm getting this t plus 1 should be equal to, what should it be equal to? It should be delta t into U plus x of t. Hope my algebra is not wrong, right? So what is this? This is just the discretized version of your dynamics. Okay. So think about X as any signal, any state, any system, whatever you want. This is just for the mathematical aspect of it. So you could get a feeling of where we are heading. Okay, so this is the dynamics, and this is a control, a problem that we all know. What I want to do is ensure that t plus 1 goes to some point x star. So what I want is to choose a U such that my system is going to some point x star, right? Has any of you taken any linear control course? You know the answer for that? No? Okay, very good. You don't have to, okay? But all I'm going to do is a little bit of a massaging and you'll see what happens. So let's assume I take this control or this value for U, which is some k into x star minus x t. Okay? This is some error. And this is some, I don't know, I just pulled it out of thin air. Magic. Okay? And then I'm using this control now. See, note that the objective is to take xt plus 1 to x star as time approaches infinity. To go infinite time, you want to do that. Okay. So if I plug this, so let's say this is your 1 and this is your 2, and if I put 2 in 1, okay, all I'm doing is substituting and linear equations, nothing fancy. Xt plus 1 should be equal to delta t into k x star minus xt plus xt. Okay. Stop me if anything is unclear. Most likely my handwriting, but other than that. Yeah. I just substituted 2 in 1. I'm going to do one more thing before we proceed and we analyze and whatever. This together k and delta t, I'm going to assign a new variable called alpha. Okay. One more step, parallel. Then we get the final equation xt plus 1 is equal to x of t plus alpha into x star minus x. Very nice equations. All I have to do is I run this algebra, but what is with this equation? Now, remember that we wanted to do this. Ensure that xt plus 1 at the limit of t going to infinity, you want to reach x star. So let's apply a simple analysis, right? So this is my dynamic xt, whatever is on the left hand side, and then the right hand side. Now let me define an error signal such that define at xt plus 1 minus x star. So this is just a new definition, and nothing from the previous equation, just a new definition. And what I want to ensure is as time goes to infinity, if the error is going to 0, then that means if error goes to 0, this means xt plus 1 will be equal to x star, right? That's what we initially set out to solve for. Okay. Or in other words, if I now substitute, let's say 1, 2, 3, and this is 4, if I put 3 in 4, then the new dynamical system or whatnot is just gonna be et plus 1 should be equal to 1 plus right?
1 minus alpha times.
I trust your algebra. Okay, that's what it is. Okay. Why all this? Why all this? Now I'm applying, and then I think, let's say it's t plus 1. Now let's say if I apply this to t plus 2, okay, then recursively, this means it's going to be 1 minus alpha into e of t plus 1. And then this is going to be 1 minus alpha to the power t square e to the power t, right? Which means after n steps, the error after n steps, it's not suitable, but error after n steps is simply going to be 1 minus alpha to the power n into whatever initial condition you started. That's all you care about. Okay. So let's say if I gave you some initial condition and you propagate this in future, after n steps, this is the error you're going to get. What we are interested in is in driving this error to 0. Or in other words, limit t approaches infinity. What is e of t plus n? Okay. Look at the right hand side. If n approaches infinity, what happens to this term? So 1 minus alpha to the power n, and we're interested in n approaches infinity, that's like forever in the future. What happens to this term? Right? If 1 minus alpha is less than 1, right? Or in other words, this exact term is less than 1, then this is going to diminish. Or in other words, as n approaches infinity, this goes to 0. Right? This is what we wanted to do. So, at the limit of n approaching infinity, this exact term here, 1 minus alpha goes to 0, which means this will be 0. Or in other words, e of t plus n is equal to 0, which implies x t plus n is equal to x star. So this is the limit result. Or in other words, I did some massaging. I chose some u, something somewhere, right? And then at the limit of n going to infinity, if I take n steps following those dynamics, I'm able to tell you that the x reaches x star. Okay. What the hell does this have to do with reinforcement learning? We are doing something probably somebody does in some ODE class or even some algebra class. But why are we interested in this at all? Turns out, the learning group or the so-called fancy terms that you will see, so many terms, PD learning, temporal difference learning, bootstrapping, all these things, just boil down to this one simple rule. Okay? This. Or in other words, let's say if I have a target for xt plus 1 to reach, or if I want my x to reach x star, which is my target, if I iteratively follow this equation, if I have certain conditions on alpha, I'm guaranteed that my t plus n will go to x. Let's look at this again. There is a target on xt plus 1. This is x star. And then here is the dynamics that I concocted. And at the limit of n approaching infinity, meaning you recursively do this n steps, then you're bound to reach x. Let's think about it for a minute, right? So we just did something on alpha, and then magically x went to its target. That is for a point, right? Or at least for a state and a first order system, right? That you guys are familiar with. Also, that works for a function. This is the central learning rule of reinforcement learning, right? So let's say now Q is some arbitrary function, and I want it to approximate or reach a function g of x. All I have to do is iteratively follow this learning rule. See, it's exactly the same as what I wrote in the board there, where Q of k plus 1, which is the iterate or version of my function at the k plus 1 step, is going to be whatever is the value of my function or the iteration of my function now, plus alpha times target minus my current approximation or my current function iteration, right? That's it. This is the one rule that people were dwelling with for probably 5 to 10 years, right? And calling it with all these terms. But depending on the context, this is just gradient ascent, gradient descent, whatever you want to call it. Okay. Let me skip this theorem, right? For those who are interested, I'll explain it later. But that's the first rule that we need. Somehow to learn a function or to make a function go and reach a target function, that is g here. Okay. And the second thing that we need to know, or the second idea that is core for reinforcement learning, is sample mean approximation. What does that mean? What does that mean? Remember the symbol from before, the expectation. So x is a random variable. And if somebody gave you the distribution or dynamic, then you can exactly compute this integral. Or if you're a skillful mathematician, you can do that. I am not. So that's in the continuous setting. So the expected value of x, and that's the continuous setting. And in the discrete setting, it just becomes simply or straightforwardly becomes a sum, right? This is what mathematicians always do. They're behind, they try to compute. But engineers, we can play a slight trick. Remember the notion that I mentioned before, the expected value is just nothing but on an average, what is x? Or in other words, if I have n samples of x, right? So let's say I'm tossing a coin, I'm throwing a die, I have n samples, then the average or the expected value of its outcome is just going to be the sample average, or add all of them, add all the samples divided by n. This is literally average. See, as an engineer, I can do it. Or in other words, I'm doing an approximation of the actual expectation. That's it, right? So depending on the conditions of x, if x is IID and everything, there is like the law of large numbers, central limit theorem, big things, right? But I'm stating it very informal, right? So that we're comfortable with whatever is there for us to store. Okay. So the theorem informally, whatever I said or whatever I wrote, is exactly the rough proof of it. There are two conditions. It says if every state action path, so think about the reinforcement learning problem again, where you have states, actions, and you are interacting. If you infinitely visit all these paths, then Q approaches Q star. Yeah, there's the second point, is not important, it's just some conditions on alpha. But think about it for a minute. It's saying that you need to infinitely visit every state. How can I infinitely visit every state? What does it mean? Right? So the problem there, that's exactly the exploration thing. That's where the theorem comes from. So I told you the exploration was exploitation trade-off, right? If you don't explore enough, or in other words, if you don't visit all states action paths, you won't even know what is the optimal, what is Q star. So if you visit it infinitely often, you are bound to explore well, and then you can guarantee this. So that's what the theorem is informally telling us. Okay. That's the only theorem you'll see in this slide or in this entire lecture moving forward. So that's about it, right? So that's the only backbone of why RL works. Okay. Okay. Some definitions, and then we'll have the final algorithm, and we'll jump quickly to code. These are the two ideas. Just remember these two. We have a learning rule, we have an approximation. Let's go.
The equation that you gave for the learning rule, does that apply to both the branches that you showed earlier in the diagram? Because earlier you were talking about how one, it's model-based, one is control-based, right? And this one requires knowledge of the model.
This is for model free. The people who did this, you see, there is no P here or dynamics here, but they're only talking about how to update my function, value function. Okay, so the return of value functions. Okay, I define something in optimal control very naively, very, simply. But then reinforcement learning people decided that we need to have something different than optimal control. If not, we need to call it optimal control, right? So they tweaked the definitions a little bit. I mean, of course, I'm joking. There is more to it. But nonetheless, the definition of value function is a little different here, and it has more of an intuition purpose than a rigorous math. So you see here, it's the expected value from your current state. So let's say your state is x dot, it's x, and then you're using your controller, you're following your controller pi. What is the expected value of this returns, right? There is that one weird symbol I explained in a bit, but let's look at a cartoon. Okay, so you're in state x, okay, and then you call the controller and say, hey, pi, what should be the action or control I should be applying here? And then it gives you u, and then you apply x dash. Then the value function is going to tell you how good or bad it is to follow the controller pi forever, right? Meaning at x dash, you call the policy again, and x dash dash, you call the policy again, and you continue forever. The value function is trying to gauge it. It's trying to compute it. It's trying to measure it. How good is it to follow pi? Okay, that's good. Nothing new. This gamma, let's forget for now. Or in other words, it's just it's a numerical trick, so to speak. Not very important physically, but that's the physical interpretation that you need to have. There is a slightly tweaked definition that RL people really love. Or in other words, I said Q learning, but we just saw V and pi. Where did Q come from? That exactly is the next value function. Now you see the input is not just X, but also U. What the state value function tries to measure is starting from state X and some control U. Somebody gave it to me. And then I follow pi. How good is it? How good is that a decision? Or to going back to our cartoon figure, you got an X and U. Somebody told you that you're in state X and you're supposed to apply action U. Came from some policy, someone, I don't know. Went to X dash, and then you're calling the controller, right? So from X dash, you're calling controller pi X dash, right? And then you're following the controller forever, policy forever. Then Q tells how good is it to follow policy pi starting from the state action path, X and U, right? The difference is very subtle. To an extent, when I first saw it, I was like, what is wrong with this kid? They just like to write these fancy equations. What's the point? What's the point here? It's like, okay, so you start from a state here, and then you follow the controller forever. Here you start from a state and a controller, and then you follow controller. Then you follow the given policy. Turns out the difference is really big. In terms of definition, they're exactly the same. You can use the same dynamic programming equivalently. You can use either of the functions. But when it comes to learning, there's a difference. But one thing it's good to know is the relation between them. I think that kind of is what made me understand it. So you can think about V pi, which is the value function from state X, as the state value function starting from X and using the control pi. If it's confusing, you can forget it for now. It doesn't matter. But it's saying, hey, you said that somebody gave me X and U, and then you're following policy. But what if the initial U itself was from pi? Then that's nothing but the value function origin, right? Because here U itself was from pi. So this is the relation here. Yeah. Why do we even care about all of this? This is something you need to really get into. When you work with it, when you write the code, and when you see your learning agent is not learning, you will be really sad. Okay? But this will be the exact reason. The reason is when you try to learn this function, V with the learning rule and all this math that I wrote there, it leads to a biased estimation. Or in other words, it's a bad learner. Right? Eventually, whatever it converges to, there is always an error. It's not good, right? But if you do this small tweak, and then you do learning, because learning is, see, that we are accumulating compounding approximation. Every time you do an approximation, the error is compounding, but this estimation is unbiased. Or in other words, Q converges arbitrarily close to Q star. So let's say V minus V star, there will be some error, but Q will converge arbitrarily close. That's all there is. So for the people who, since you guys are first seeing it, all you have to take from this slide is learning Q works, learning V doesn't work. See, all the rigor went out of the window. It just is because it's working. Okay, that's all, guys. Okay, 3 algorithms, then we go to the code. Here is a solution. As I said, data, right? So somebody threw your agent in your environment, and your agent was doing some actions, I don't know, right? And it gives you these trajectories. Okay, note that there are L trajectories or L interactions with the environment. So let's say you started from some X naught, you are doing some actions, you get, well, let's say at some xt, you apply some ut that your agent did, and then you got a reward rt, you're going to xt plus 1. So there are L such trajectories. Each of them are t steps long. This is important. I assume that there is a finite length to this trajectory, which may be very obvious for you and me, right? But that's need for this algorithm. With this, we are trying to solve the first problem, or the first algorithm, which is called Monte Carlo control. What is this? What is this? So we start with some alpha. Like remember this, your alpha, right? It has some conditions to satisfy, greater than 1, whatever, but there is some alpha. And then you initialize your tables and whatnot. Then for each trajectory, like over there that you see, right? So or for L trajectories, right? You take your current controller, go to your environment, get a trajectory, right? Or in other words, you took this one trajectory. You took your controller, you got this one trajectory. Now I completed the trajectory. I have the entire trajectory, and I want to compute, or I want to update my policy, right? Such that it's performing better. Or in other words, what I would do is, let's say I have the first trajectory from some state xt, I will compute what is the integral over the rewards moving forward, right? So let's say rt plus 1, rt plus 2, all the way till r capital T. That's the expected returns, right? From that point in time onwards, right? So that's my GT, or that's what I want my value function to track. And then I'll do this update. Let's take a step. You see, what I did is I computed a target function. So the function is supposed to be from given state X, how good is it? Means like whatever rewards I got, right? So because this controller is what led to this trajectory, and this trajectory led to this integral, right? So my Q value function should reflect it. It should say from this state X, if you follow the policy phi, this is the value, or this is how good or bad it is. So what a Q function is doing is trying to learn that GT. So GT is your target. Q is my QK is my current approximation of the value function, and then I'm using it to get my next value function, right? So QK plus 1 is equal to QK plus alpha into target minus current. Exactly this equation. And then if the conditions are satisfied, the weather is good and everything, right? Then QK plus 1 will go to this optimal value function, thanks to our amazing theorem. Okay. And then I apply my controller. My controller is like before. If you have the value function, then the controller is just the argmax of QK plus 1. Don't worry about the math. I've explicitly written it in this high level fashion, so you get an idea more than the exact computation. But then you do this. That's it. Right? That's all your algorithm. Generate a trajectory, compute the target, update your value function, update your policy, repeat. And then you do it for L trajectories, 1, 2, 3, 4. Towards the end, you have a policy, right? Now, what is the problem with it? So this is reinforcement learning, right? Because I'm collecting data, using the data to update my policy, right? What is the problem with this? You guys see any problem or any doubts at this point now to the time?
I'm confused as to what exactly is R.
R is the reward. So the first step cost, right? So if I'm in XT and I'm applying U, the environment tells you, hey, here is RT, here is the reward. And then the target is nothing but the reward forever from that point. So RT plus 1, RT plus 2. So that's this again. And the value function has to learn that. That's this target.
So in what you wrote up on the board, your X star was like your desired state,
Yes.
but
Target.
right, yeah, so target state, but G of T in this case doesn't necessarily like what's the analog
Yeah.
there?
Yeah. So I made a very discrete jump. That was X, XT, state space, whatnot, but G is a function. So all I want you to believe, almost like an axiom, is whatever I did for these points, whatever, works for functions as well. So the analog is here, you see X star is some point that I know exists. I don't know how to get there, but if I do this iteratively, I get there. Similarly, here GT is the target function, because you see what GT is telling you. You connected the trajectory with pi k, and when you compute this, it's telling you how good was that controller, right? So what I want my value function to reflect is that function, right? So my value function should learn that GT or should approach that GT.
I guess it might be a double question, but why do we want a value function to learn the GT? So like I understand that it's like it's a sort of reward for using that particular controller for the entire time segment.
Yes.
But having wide why is that you're doing learning? I guess like, it might be.
No, there's nothing dumb about it. In fact, if there's anything dumb, it's this equation. Forget it. Let's say this equation was not there. How would you go about improving your policy? So you got the equation. Now you think, okay, so you're saying this learning may not be done. Let's assume that's the case. Let's throw it out. Somehow I need to update my controller, right? Because the original pi is resulting in GT, but I want to learn, I want to be better, I want to improve my controller. How will I do it? So here learning the value function is my mechanism to know, hey, here is how good or bad this policy is. And this is the exact mechanism which tells me how to update my policy.
But you're learning, like, essentially, aren't you in a sense sort of rewarding just that particular control point?
Yeah, so that's pi k. Pi k gave me data.
Right.
Data led me to update my value function to q plus 1. And k plus 1 gives me the next policy, pi k. Right? So this principle, this learning or whatever is from that, because we know that we want to ensure that we are tracking this GT somehow, because and then we are updating it. And then we are using that update policy. Right? There are a lot of things I'm hiding there. But you know, again, if I open this up, that's a whole new can of worms. But anyway, as long as the intuition is clear, you'll come up with better questions later. But the biggest problem here is I said all this philosophy and everything, where I said reinforcement learning is this double-edged sword, there is exploration, exploitation. Where is exploration? There is no exploration. We're only doing exploitation, right? Because every time you learn a new value function, you are just being greedy about it. You're saying, hey, what is the action that maximizes it? Meaning, if I start with a controller pi naught that is really bad, or it's stuck somewhere in the environment, and let's say all these trajectories are not good data, bad data, then no matter how long I do this, pi k will never improve or will never be a good controller. So to speak.
We kind of assume that initial policy is stabilizing.
That's one way to put it. That's the real analogy is not good. It's a lot of trouble there. The analogy, we can do it offline. But what I'm saying is pi naught gives me good data. It's an assumption. Whatever that good data means, I don't know. But intuitively, does it make sense? Right? Means that these L trajectories allow me to improve my policy. That's what I mean by good data. If pi naught is such that these, let's assume that pi naught you put in the environment and all N trajectories were the same trajectory. Let's assume. Then if you do this, it will not improve your controller. You'll get pi k plus 1 to be pi k. Right? Then you don't learn. So we assume or whatever this is, we say pi naught somehow gives me magically good data. And then if I'm being greedy with respect to my good data, success. But the real world is unforgiving. Doesn't do that. Not success. See, greedy in nature. Don't be greedy. Bellman taught us. Okay. So there is no expiration, but there is a tiny fix. And I really like the tiny fix. Okay. See, so this is exactly the algorithm that I constructed step by step. Now we do one change. Okay, just so that I got this right. Instead of updating my policy, where I say, hey, be greedy with respect to my new value function, I'm saying, let's say you can be epsilon greedy. Or in other words, what does this mean is, it will update the policy pi to have the optimal action or greedy action with 1 minus epsilon problem. Epsilon is like some small value. But if not, it's going to take some random action. Okay. Or in other words, I compute all of these things like before, and then I update my policy. I toss a coin, or like I throw dice or whatever, and then I see some epsilon. And if the probability of that, or if it falls below 1 minus epsilon, then I use the update my pi to be greedy. If not, I make it choose a random action. Rightly named as epsilon greedy strategy. Right? So now you see, for this amount of probability, it's going to take random actions in the environment. Meaning, if I update the pi k plus 1 and go to my next iteration and I collect data, this policy will be taking some random dumb actions. Okay? Means what you're going to end up is the next trajectory that you get will be quite different from this, at least. Right? We don't know whether we're exploring well or whatever, but at least it's different. Because you see, you're not just being greedy, but you're also introducing some randomness, right? So the new controller is just going to take some random actions, meaning different enough trajectories, meaning you get good data to it. Exactly. At least is the idea clear. Yeah. That's stupid. In the sense, yeah, sorry.
Sorry, what is capital U?
So capital U here, if you want the exact answer, that's just the dimension of your actions. So if there are n actions, this is going to be n, right? It's the cardinality of your U actions. All this is saying is you will take the optimal action U star, which belongs to that set. It has 1 minus epsilon probability, meaning the remaining probability is equally distributed among all the other actions, right? So it's a uniform distribution with this much probability, epsilon by 2. Okay, where was I? Yeah, stupid, right? Just because you don't know how to explore or how to get better data, you just are taking random actions, which is almost the worst thing to do, right? Imagine Hector. Yeah, I put Hector here in this room. I have this fantastic algorithm, and I'm telling him, hey, walk to learn. Sorry, learn to walk, right? Start time equal to 0. Hector is like this. Button is on. Does random actions, face plans, and then the professor is really angry, right? You probably costed him, a lot of money, right? Algorithmically speaking, this is one of the dumbest things to do, right? So that's why it's a strategy or a heuristic. It says, hey, we don't know how to explore well. Just take random actions. Let's see where that goes. Okay. But as I said, RL, we don't know anything. So let's be, this is the best we can do probably. Or at least this is what people thought they could. Okay. So 2 points here. One is note that this is very important. Something called on policy. What does it mean? See, the policy pi k that I'm using to collect data is the same controller that I'm updating, right? So I use pi k, the kth iteration of my controller, and then I use the same to collect the data as well as do an update. Okay. So that's what this means is you're using the same policy to collect data as well as you're updating that policy, which is the most intuitive way to do it. Doesn't mean that's the only way. We'll see it in the next slide. And then another very big drawback is, you see, we can do learning only after the end of one trajectory. Meaning, if you give me one full trajectory, that is this entire trajectory, I can do one learning update, right? One trajectory results in just one update, which means I need more trajectories, which means it's computationally heavy and everything. But you can only, so you see the sampling efficiency, the learning efficiency is not really good, right? So for one trajectory, you're just learning once, right? So this really annoyed people because they needed more trajectories and everything. That led to the final algorithm, which is the star algorithm. And after this, we'll go see code, right? Some nice GUI and whatnot. So imagine this set, same trajectory, right? But people now said, I can't wait till the end of the trajectory, right? I have better things to do in life, right? So in state XT, you took some UTR and then you got some, oh, sorry.
Oh, I had a question on the last slide.
Oh, sure.
So it seems like your update equation, like it's just kind of like this relatively simple pattern of creating a better and better policy, right? But then you're saying at sometimes we don't really want to follow that pattern, and we just want maybe a non-optimal or a non-most rewarding policy, and we do that, and then see what the
That's what I'm doing. But the question is not what I'm doing. The question is why am I doing it?
Right, that's what I'm trying to.
So the so-called pattern that you said it's going to improve. What is the disclaimer then? It's assuming if you have good enough data, then you improve.
Yeah.
But what if the data collection resulted in, so that's the example I gave you.
Yeah.
What if all the trajectories were the same? There is no improvement.
Yeah.
That's the dual problem.
And that's the reason why you sometimes will use a random.
Exactly.
Okay.
Because the dynamics is stochastic, right? So to explore, I have to take some random dumb actions, right? So imagine there is this one famous, it's called bandit problem, whatever. Let's say in front of me there are 5 doors, okay, and behind one is some pressure or whatever, right? And then I have like a very good prior or something which tells me the third one for some reason. Nikola Tesla said so. 3 is the magical number. I'll open the third door, right? And that's a heuristic, whatever. But then I don't know unless and until I open the other doors or explore, I won't even know where the measures. The same analogy.
Is there ever a point where you like just stop doing those random things because you're policy that you have is just
For the same person, yes, that's what you should do. So what people do is as L increases, they decay this epsilon. So let's say you start with some epsilon, 0.1. For every new trajectory, you decrease the epsilon. 0.1, 0.001, 0.001. Towards that, a last step, you'll probably be purely greedy and not. So maybe I was too hard on it. It's not stupid, but could do better. We could do better. Okay. Last algorithm before code. The problem was we need an entire trajectory to update, do one learning update, wasteful of sample, right? So what people said is I can't wait till the end of the trajectory. So I'm in state xt. I applied ut rt, and I got a state xt plus 1, and I got ut plus 1 and rt plus 1. Just one transition, not the entire trajectory, one transition. With this one sample, can I learn? So the question they're asking is, can we learn from this one step interaction? So remember the agent environment setting. In the previous setting, we did this for t time steps. And then from one trajectory, we did one learning. Here people are saying, let's say I did one interaction, I got one sample. Can I learn from this single interaction? I don't know, I won't wait till the end of the trajectory, but like a single step of the trajectory. What do you guys think? Can we?
Like elements up to that like principle. The step from K to K plus.
Everyone in this class is smarter than me. Yes, yes. The only problem is you can't exactly compute Bellman. Why? Sorry, Bellman is the right idea, but you can't exactly compute Bellman. Why?
You don't have the dynamic.
You don't have it. Model is there, then yeah, Bellman did it in 60s. What are we doing? Very nice, very nice, very nice. Makes my job very easy. Yeah. So what people said is, there are two problems before. That was that one policy, the same policy was used to explore as well as update. Right? So people introduced a new policy, PyB. I'll explain about it in a bit. This PyB. And whenever we collect data or take a step, so do note that we're not taking a trajectory, we are just taking a single step. We'll do it with respect to PyB. Why is this important? There is no limitations on PyB. You come in one day, you give me some absolutely insane PyB, some controller I don't know anything about. This algorithm is fine with. Because we are collecting data, we are allowed to collect data with any controller. It's called a behavioral controller. So we collect a data or a step sample with PyB. And here is what we are going to compute. Previously, recollect, this was an integral over the entire trajectory because we had the entire trajectory. Now we don't have the entire trajectory. So now this is exactly what people said they are going to do. Looks exactly the same as Bellman, whatever was inside the Bellman equation to me, right? With one and only difference. Because in Bellman, you can compute this term exactly, right? So this is the RT is the first step reward or cost or whatever. And after that, you can exactly compute this as an expectation. But now you don't have the dynamics. So what people said is, instead of computing the expectation over xt plus 1, exactly like Bellman, I will just plug in whatever was my previous iteration. And they have a good fancy term for it. That's behavior policy. They call it bootstrapping. So what they are saying is, hey, I don't know what the exact optimal value function is because I don't know the dynamics. So I will just use whatever I thought previously was the optimal value for that state, or whatever was my previous estimate, the previous iteration, QK, whatever was my previous iteration. I'll just use that. So we are estimating an estimate with my previous estimate. You know, so the first time I saw this, I was like, what? What the hell? We are updating. Okay, let's take one step at a time. Here is the update now. It says I'm going to update my cube k plus 1 based on my current estimate. Good. But then there is this target function, which is supposed to reflect the function that I somehow am inferring from my data. Good. And then you go and you make the target function itself depend on your approximation. Right? No reason for it to work. It's called bootstrapping. Where you take your estimation and then use it as a target. But psychologists said that's what the brain does. Okay, so this is called as a temporal difference error, or exactly what Bellman's math told us, only an approximation of it. So now you guys should hear in your ears what Richard Sutton said. Don't approximate the problem, approximate the solution. That's the philosophy right there in action. So he said, yeah, I know, but let's see what happens. Okay? Let's just put the estimate and see what happens. It's an approximate solution. That's okay. Okay, but now the good thing is it's an off policy, meaning I can use PyB, any controller you want to collect the data, and then I can independently update my policy. So what I've done here, another thing is, I've outsourced my exploration to PyB. So PyB could just be a random policy, whatever scheme you come up with, I don't know. But the algorithm, all it has to do is based on the data that PyB collects, the interactions, it's going to keep updating the optimal policy, which is k plus 1. Right? Is there anything else? Yeah, that's about it. So let that sink in. 3 ideas. Behavior policy, which means you use any controller to collect data. Bootstrapping, which means you just make your target as a function of your previous estimate. And temporal difference error, just a fancy way to say, hey, I just care about this one step error in time. Then you do that, you get this algorithm called QLearn, which is what we're going to see in action right now, right? But this right here is the algorithm. And you'll say why we did all these magic tricks.
What happens if you're not using 5B, but if you're using your same policy? Is that
It will still work. It will still work. Meaning, as an algorithm, it will boil down to whatever you saw in the previous slide. Does that make sense? Because if you take pi b equal to pi k,
Yeah.
and let's say instead of this, you take a different target or whatever, you are just going to end up with the previous. So when you use pi b, it's a separate policy, they call it off policy. Meaning you can collect data with any controller, but you can still learn the optimal control. Does that make sense? Right? But again, as I said, pi b could be anything, which means it could also be pi k. Totally fine. The algorithm is agnostic to it in a sense. Okay.
Still everything is working on only one trajectory.
One step in a trajectory. Previous guy was working on one trajectory because you see the target was integral in future. Computes the entire integral. GT is just computing one step.
I mean, you run this, you are running this on a one trajectory. You are not looking at.
I'm looking at one step. You see, previously here I collected an entire trajectory and then I compute GT. But to compute GT now, I just need one step. Right? So this can continuously go for on and on, meaning there may not be even a finite episode length. That's why you see there's 3 dots there. At time t equal to 0, I start, right? And then for every step I'm learning, which means it doesn't matter how long the trajectory is. You can go learn on and on and on. The term that they use is called continual learning because you only need one step. Think about it this way. Time t equal to 0, Big Bang, God said that there be light. Humans have been evolving since then. This is the aspect that they wanted to get in their algorithm. Continual learning, learn forever, right? There's no switching. Okay? Yeah.
so if you're trying to design a controller that's trying to do multiple different tasks, how does that expand into?
It doesn't expand. So if you ask Rick Sutton, the guy with the beard, he tells you, hey, multiple task, single task, as long as you give me to me as a single reward function, I can solve it for you. That's the reward hypothesis. But it has no rigorous mathematical basis. He actually did his bachelor's in psychology.
In a sense, is this algorithm also greedy because you're using the best possible value function for your bootstrapping from what you know. So
You mean this guy? This guy.
no, in your GT, when you're computing GT, you're using the maximum value function from your previous.
So
aren't you?
okay, so this
By
doesn't
virtue.
make an algorithm greedy or epsilon greedy or whatever. It's this control update that makes it greedy or not. Or in other words, this is just I think you are the one who used the pattern or rule or whatever, how to update my queue. Q just tells me in this state X, if I'm applying action U and following the policy, how good is it, right? So that's no greedy enough. It just is a matter of how you collect data, right? So here, as I mentioned before, we are outsourcing the data collection to some other controller, which you give us an input to my algorithm, right? So this update on whatever, it only has to be greedy because the epsilon exploration part has been outsourced to pi b. As long as pi b is exploring well, we're.
Is pi b a control policy or just the first control input? Because aren't you changing?
Okay, that's a good question. So you see this k that you're seeing here, and this is b, meaning b can be fixed. It's a controller that's given to you by someone, right? And it's just saying, hey, collect data. So think about it this. Right? This is not a very good analogy, but this is what I could come up with. Think about pi k as a student, okay, and pi b as your teacher, right? So the teacher is telling, okay, when the student is trying to learn, let's say you guys try to learn in this course optimal control, Professor Kwan was telling you, hey, here is some equations, here is something you need to know. And then you go and improve your skill in that, right? So this pi b can be fixed. Pi b need not be learned. Pi k and pi b have no connection. Okay, pi b is just giving you the samples that you need to learn, right? Pi b is not even being updated; it's fixed, right? It's like a teacher; it just gives you the samples that you need, and then pi k is just being a good student. It's just learn.
But do you continue using IB after the first update or not?
If it works, use it. Not don't.
Sorry?
If it works, use it. If not, don't. In other words, yeah, people play tricks all the time. So for the first few steps, they use pi b, then they don't use pi b. They have if-else conditions, all this very nasty, no guarantees and everything. Works, keep it. If not, doing it.
Does pi k eventually become pi b if you keep counting it?
Maybe. So going back to my analogy, maybe if you learn enough, you'll be better than Professor Kwan. I don't know. Could be the case. Depends on how good the learner is.
I'm confused where the original like Q is coming. It's like
Ah.
you're saying you compute it based on some previous estimate, but then if you're always basing it on previous
Yeah.
estimates, when does it?
Okay,
make
can you
sense?
wait, like bear with me until the next slide, when I see the
Yeah.
code, you'll get it.
Is that controller the MPC,
Fine B?
whatever you learn, but or data gathering?
So the answer for that is, you see, if you meddle with it long enough, you will see that whatever I've shown you, and MPC is really the same thing. At every time, let's say you're at some state X, you're finding bunch of trajectories and choose the best one. Exploration, exploitation, whatever you want to call it. It could be, yes. So MPC will just be one abstraction of it. Think about it this way. Let's say it's still MPC, but there are parameters to MPC that I want to learn or tune. I can use this update law, right? I can just tune. Pi k is my current version of my MPC gains, Q and R, whatnot. And then my next version, I change the Q and R, I tune it. So instead of you manually sitting and doing it in MATLAB, this will do it for you. It's just a learning rule. It's agnostic to the problem. Throw any problem at it. All right, to solve. Okay, good. Oh,
Correct me if I'm understanding this wrong, but how do you implement a goal? Say you have an end goal you want to reach, how does that play into?
oh, for this guy?
Yeah.
Good question. I don't know. So in the previous setting, I think it was just XT, X capital T, right? Here, so when you say goal, implicitly you're saying it should have finite end,
Exactly, yeah.
right? So my best answer would be, you should use the previous algorithm.
Okay.
But if it is something like an asymptotic goal, right? So let's say you become the president of US or whatever. It's an asymptotic goal. It's not going to happen in a finite time. Maybe eventually you will or whatever, right? In that case, I would say at every time, as long as your reward is guiding towards you, asymptotically you will. So for anybody who's more familiar with the control literature, control itself is an asymptotic problem because stability we don't know when the stability, whether you will be stable in one step, two steps. It's not a finite problem. It's an infinite horizon problem.
Where do you see this algorithm usually applied in that?
In practice, we'll see. I'll show you an example. So all this is, this is for you guys to get a good feeling about learning. That's all it is. There is no magic here. There is no, fancy things going on. It's just good old learning rule and approximations. But all this is applied only to tabular. But the last part, which is the last 20 minutes or so of this lecture, we'll see that in action. Okay, time to code. Time to code. Once again, this will be available to you, right? So you feel free to tinker with it. So in this, there is a nice problem called taxing, right? And as the name suggests, it's just your good old lift or whatever you were there, but it's a very simplified setting of it. So there is a world where there's a grid world or whatever, right? So it looks something like this. I'll show it in a minute. Your taxi starts at some, so imagine that this is like a discrete graph or like there are just like points, and in one of these vertex or whatever, your taxi starts, and then your passenger is at some point. Let's use an X for a passenger, and you would like the cab or the agent to go pick up the passenger and drop it in some location. Let's say this, right? That's it. It's a very simple tabular settings, and that's what we are going to solve now with QLine. Yeah. So for this, once again, don't be afraid of Python. It's not going to bite you, right? It's the exact same thing. All you have to do is press buttons, start tinkering it little by little. You'll be comfortable. Okay. So thanks to Google, I don't have to install anything. Let me just press connect. I'm going to get the power of amazing computers connected. Good. So all this thing is doing is importing some modules, right? So in MATLAB, I think all of this is installed and pre-installed for you. In Python, you just have to install it, right? It doesn't take long. It just takes a couple of seconds. Okay. And then, So previous setting, I gave you P, R, L, and everything. So the matrices were given to you, right? But here, what was the assumption we made? We said that nobody gave you P and R, right? If P and R was given, I can just do iteration. So to preserve this black box structure, there is a module called gym. All this gym is going to do is, it's going to make an environment for you, and it's going to keep it black box. Meaning, it's not going to tell you what is happening inside the environment. It will only give you the observation and rewards, so to speak. And as an algorithmist or whatever, it's upon you to use that reward signals and learn and whatnot. Okay. So here I'm just calling Jim and saying, hey, give me a environment, right? And the moment we throw this, the first question we have to ask is, what are the signals? What do the signals look like? So in this is a tabular setting, which means there are finite number of states. So if so it says that the number of states is 500, or in other words, these dots that you're seeing, there are 500 of these points in this world. Okay. And then the number of actions is 6. I don't remember what exactly it was, but most likely it's going to be directions. Yeah. So 4 directions and pick up and drop. So that's the 4 actions. So as a taxi, you are allowed to go in 4 directions. And then one more action is whether you can pick up and the other is drop. Right? So before I even run you through the code, it's just one block. And here I've just exactly implemented the equations. I'll walk you through line by line, but it's always better to see animations. Okay. So here we are learning, give it like a couple of minutes. Wow. Time t equal to 0, our taxi driver sucked. He had like minus 3,000. So here it's rewards, so we're going to improve it. So he was a really bad driver. The customers gave him 1-star rating and whatnot, right? But from that rating and whatever he learned to be a better driver, and eventually his performance improved. The reward curve increased. That's what you're seeing, right?
Sure, so like what criteria are we saying is good? Like,
Yeah, I'll walk you through that because I skimmed the code for a reason, because I want to actually show what this looks like. Okay, so now I've trained the controller. Whatever this Q, whatever you saw in the equations are done for you. Okay, let's assume that. Now let's just evaluate it. Let's see what our driver is doing. Oh, that's what he's doing. Okay. After all our equations, I'm happy to see this GUI, right? So we start at this point. This is the a point, right? And from this, you see, who's slow drive? Yeah. So here is the passenger, goes, picks them up, and he takes the optimal route, just following our good old learning. Then he's able to drop without knowing anything about the transition model. The Q learning doesn't know whether it's a passenger, whether it's a building, whatnot. It only knew this one criterion that he was interested in. And by just learning by trial and error, he's a very good driver, right? So now you see, I'm gonna tweak this a little bit. So you see, the initial condition was, you see the taxi started somewhere, but you know what we can do? We can change this initial condition, right? Or in other words, I'm saying, hey, taxi driver, you're starting somewhere else. Let me run this again. See this? Now he starts from here. See that? So that's the optimal path he learned. So this is only because we are not thinking about it in an open loop manner, where we are hard coding all the solutions. But by doing learning with this dynamic programming kind of structure, but with approximations from any initial conditions, we are able to go solve the task, right? And here there are some metrics where we say the total reward is 5, whatever that means. And then we have some penalties, and nonetheless, the task is solved. Recollect what I showed you in the first couple of slides. At times, we don't care about guarantees and proofs and theorems. What we care is whether the task is solved, whether the sauce has been applied, whether the robot is able to do it, whether the passenger was dropped in the location. Okay. And I think the best way to learn is play with it, tinker with it. All of this is for you, break the code. Okay. But since I will almost like skimmed through real fast, I just walk through these exact code so that this question gets answered as well as yours. So you see, we made the environment in the previous box. The environment is there for you. And I started like my Q matrix to be 0, 0. So S comma A. So if I put some action state and action, it's going to tell you exactly what the value is like that. It's an array. Okay. And these are the parameters that I chose. You can play with it and see what happens. Alpha was the learning rate from there. Gamma was this weird equation we had, not important. And then epsilon is the greedy thing. Okay. Here we start. We have 5,000 episodes, right? Or in other words, let's say there are like 5,000 of these interactions. They're starting with this environment, right? It starts with a passenger being somewhere and ends with the passenger reaching this point. But even though it's still episodic, the learning is happening at every step. What does it mean? So let's say we start that episode, and then we get the initial state, and then we have 0 returns because at time t equal to 0, there is nothing that you did. And while not done, so done here means whether the passenger reached this location or not. While it is not done, this is the epsilon. If this random probability was less than epsilon, what do? Take a random action, right? Because we're exploring, collecting data. If not, we are using the whatever we think is the best action type thus far, which is the argmax of your Q. Don't worry about the code, but just follow me through the idea. So we do this, we apply the action into env.step, which means you apply the action, then the environment is going to say, hey, here is your next state or the observation, reward. Okay, that's it. It's not telling anything about the transition dynamics. It's just giving you these 2 signals. Now, for that one step interaction, literally, you give an action, you get a step, you're updating or you're learning. And this exactly is your learning algorithm. So it's your current reward plus gamma times NP max. This was the target, if you remember. And with that target, we just applied our learning rules. Does this make sense? So to answer your question, this reward, you don't even have to care about it because the environment gives you. All you need to care about is how to use that reward. And this is exactly how you use it. That's what the learning algorithm does. And then you make state as the next state, you add your return, and then you repeat, right? And to answer your question, this is where the initial queue comes from. We set it as zeros. And as we explore the state action pairs, we go to the table and we say, hey, okay, this state action pair looks good to me. Let me assign this value. Okay. And that's what this guy is doing. It's iteratively going to all actions.
If we start off with Q0 and V0s for everything, doesn't am I mistaken in assuming that wouldn't that just mean that for you're just doing like your control policy is nothing?
So the Q just means that Q equal to 0 means at time t equal to 0, I have no idea how good any state is with respect to this one. Right. Q equal to 0 means any state action you give me, I don't know. So all I'm saying is it's equal to 0. In fact, the algorithm will still work if you make it as ones. So I assign each of them equal value. So the notion of value is succinct in the sense it doesn't care what the initialization. I mean the results will be a little different, but that's not the principle. It is we cannot differentiate the value or the goodness between one state action pair and another. So by setting it as zeros, we're saying, hey, we don't know. Go and learn. And every time you interact, you get one state action pair, you are essentially changing the value, right? And then you say, okay, this state action pair seems this good. The other one looks this good. So relatively, you rank, or you say one state action pair was better than the other. And do this enough number of times, do it 5,000 times, learn an approx estimation from an estimation, but enough data, our passenger is happy. We got 5-star rating. Okay.
So episodes, is every episode unique?
Oh, I don't know. In the sense that depends on the initial condition, right? But even if it's the same initial condition, remember the Hector figure that I showed you. From the same state also, since the dynamics is stochastic, right? Most likely, it is going to be a set of different unique trajectories because the dynamics is stochastic, right? In the sense from the same state, if you apply the same action, doesn't mean you have the same trajectory. You will have multiple different trajectories. Let me draw this figure right here. You have a state xt, okay? And then your controller applied some action, ut. But since the transition dynamics internally is a distribution, okay? Every time you do this, you can end up in totally different states, right? So this could be xt plus 1. These are all possible paths. Okay, we don't know. So depending on, so the right mathematical, it's not right, but at least as far as I understand, if this distribution has very good dispersion, covariance, then it's good to expect that each of the next state will be away from each other, right? And you do this enough. Let's say at xt plus 1, I'm once again applying some ut plus 1. This will also result in branches. This will also result in branches. Okay. So if the covariance of this distribution or whatever is wide enough, then you will get unique trajectories, so to speak. But let's say this P is not so unique, then all these trajectories will be very close to each other. But theoretically speaking, they should be different because it's.
And is the code learning the environment? What if you put the taxi in a different environment? Would it be able to navigate that?
Taxi is the environment, as in it's the task.
Okay.
Right? The agent is what you coded up, right? So I gave you the environment. You coded up this Q learning, this algorithm which is exploring, exploiting, learning this matrix, right? And then it's able to maximize or solve the environment, right? So taxi is not the agent, it's the environment itself. The question to ask would be, what if I change the environment? Will it still work?
Right.
You try and tell me, right? There are other environments available. All you have to do is go here and instead of calling, so see there's taxi, gym.make taxi. If you go the documentation, if you swap a different name, there will be a new environment. And all of this should theoretically work.
But wouldn't you be training it in that environment?
Exactly. There is no magic here, right? So training in taxi if I'm a good taxi driver, doesn't mean I can pilot a helicopter, right? So you need to train again. But the point is the algorithm is the same. I won't touch anything. So imagine the MPC setting. So the task is walking, right? You designed an MPC and it's walking perfectly. Now let's say the task is backflip. Is there a way for you to design an MPC to do backflip? Probably yes, but there is no straightforward answer. Right? At least the MPC algorithm doesn't give you an answer for it, like how to design. But learning doesn't suffer from the problem. Because with learning, the design of the controller as well as the tuning is one and only the same. Meaning, if you learn a controller, that is equivalent to saying you're also designing the controller. There is a fantastic theorem behind this. It's called universal function approximation theorem. If you're interested, I'll explain later. Right? So basically, by just tweaking these knobs and values, you can learn any function. And that's why it's working. Any more questions?
So in, I guess, practical applications, when we don't have environments like given in code or whatever, and we are working on like real life applications, then it's up to us to figure out how to get a good reward, right?
Oh, you're saying you designed it?
Yeah.
Yeah. So if you want to use RL, in fact, that's all my research is how to design these so-called environments, right? So yeah, so for example, I work with making Hector play soccer, and do backflips, all the things that I just mentioned. And all I do is design environment, right? And it's really harder question. In fact, you see, this almost looks like it's a solved problem. We didn't assume anything, it's working. But the truth is, you put it into continuous engineering, which is what I wanted to do, but I don't think I have the time. It all breaks down because you see, it's simple yet ambitious. You don't assume anything about the system, which means there's no free lunch. You have to pay the cost somewhere, and you'll pay it in performance. So all that we are doing in the frontiers of research, quote unquote, is how to design environments, how to come up with the right reward. Because reward hypothesis is a hypothesis. You give a reward, you will get the agent is a hypothesis. There's no theorem, right? So if I say, hey, Hector, backflip, I come up with reward function. It doesn't backflip. It just stands there. Yeah. And this exploration also is a really hard problem because here you see pi b and everything. One way I think about this is when you have finite space, it's just a table. Meaning if you do infinite interaction, you can fill this volume really well. But think about continuous spaces like Hector, that the space is infinite. How can I explore infinitely enough? It's a hard question. Regarding designing rewards, designing environments, designing this exploration, easy. These are all open questions. So maybe if you attend my dissertation talk, you'll have one good answer. Any questions? Okay. That I think we're all. I had 3 parts, but I only did 2 parts. Okay. But I think it's a good place to stop. But maybe this is a good slide. So what people knew is that it kind of works. Learning has some promise. We can learn, right? There is more rigorous theory telling when to learn, when not to learn. But people are not interested in it. People are interested in solving Atari because, why not? Right? So the problem with Q learning is that it's a table, meaning there's finite actions, finite space. But what if I want to think about continuous actions, continuous, one step at a time? So there's brilliant people in DeepMind. They said, okay, let's start with continuous states first. Let the action be still finite, right? But the input be continuous. What is an example? All of you might have played this, Atari, right? What is the input or the feedback that you get from this environment? Literally the image, right? You see this frame and you say, hey, my paddle is here, my ball is here, that is there. Okay, the observation is literally pixels, and pixels are continuous in space, right? So you have RGBA values, right? These are all continuous. There is no discretization. That's the observation, right? But then what is the reward? Just staring at you right there, right? If you get a good score, you get this goes high. If not, it goes down, right? So people took this as a problem. DeepMind people, as I said, brilliant people. They said, let's see whether we can scale up what we know from Q learning all the way to this so-called hard problem. Now, I think one of you said real world task. Okay? As a researcher, we have the luxury of hiding behind these toy problems. And it's totally fine. The reason this is a good enough proxy for the real world problem. Because if you think about a real world problem, it's really hard to study. So you have to quantify, know its limits. But if you have this simple problem, you can really study the problem, right? So they took this and they said, this is a good enough proxy for being able to learn any open-ended task. Okay, let's take their word and see what happens. So this is when I think it was 2011 or something, when deep learning was catching up. So all your neural network frenzy. So you see, up until whatever you saw right now, there was no neural network. They were all tables. We were updating tables. We were doing bookkeeping. But then there was neural networks, right? Which means magically you can reason about images. Oh, it's a dog, it's a cat. My neural network will tell me, right? So you just took a lot of dog cat images, you put it in, and your neural network is able to say, hey, this is a dog, this is a cat. We knew all the time, but now an agent does too, artificial intelligence, right? Oh, I used the word again, sorry. But anyway, so that's when people wanted to match these two. Because reinforcement learning, deep learning can differentiate between cats and dogs. Plug this in with reinforcement learning, and it was born deep reinforcement learning. Instead of tables, now they said let's throw the tables and put neural networks inside. And the exact same way where we trained how to classify between a dog and a cat, we'll say, hey, depending on your Q value, whatever the input of this image is, decide whether the paddle should move left or right. That's exactly all you need to do to solve this task, right? So it's saying dog or cat, should I move it left or right? So a neural network was sufficient to solve this problem because the input was still an image, much like a dog's foot or whatever, but the output was a classifying output. Move it left, move it right, dog or cat, whatever. Okay, people did this. So it maps directly images to control. So the control is discrete, but it's still control. And then there is nothing, in between. There is no engineering. Or in other words, you see, it's a neural network. Okay, images go in, something, and then you automatically get a action of up or down. You see, nothing else. This block cannot be broken down into these modules. Contrast this with your MPC. I think this is what I kind of hinted at. If you think about your MPC, right, you have a model block, you have a controller block, you probably have a trajectory optimization block, and then you have a heuristic, Ribot heuristic block, and they all sit in some hierarchy. Okay, and the trajectory tells you, hey, here is the reference you need to follow, and the MPC says, here is the torque that you need to control to get the system to do what it does, and this loop repeats, right? So this, I think, is called as a top-down approach, if I'm not wrong. Meaning, you think about these individual modules, design each of them, and put together for a solution. But learning puts it in steroids. It says, I don't care what this is one block. I'm outsourcing it to the learning problem. It says, hey, learn this one block such that you can approximate any such function. That's the power of it. Instead of designing each modules and tuning them separately, just learn this one block, you're good to go. That's the philosophy of end-to-end reinforcement learning. So tables, neural networks, that's where we are headed at. So continuous state space, but finite action space, right? And it was superhuman in Atari, right? So if you play, for example, here you see, just focus on this guy. So he learned to play Atari ping pong, which in itself is great, but see the strategy that he came up with. He decided, okay, if I just keep hitting this corner and open a gate or open a channel, right? Just wait for it. And then the ball automatically does the work for me. I don't need to do anything. Right? So it just manages to open this small gateway or whatever, and then it doesn't do anything. Yeah, now the paddle doesn't do anything. The ball just is dumping up. Right? This is so beautiful because nobody designed that behavior. Just by trial and error, just by getting reward signals, it automatically learned that behavior, right? By just tuning this one block. That's the power of learning. Okay. But here, for the theoreticians in the group, we really dissatisfied because it didn't work like Bellman, where there was a very sound theory, and then that's what caused the results, but many heuristics, right? Or in other words, the people of engineering, do your engineering job. Okay. So there are a lot of ideas. There is no point in going into each of this, right? But one trick that they came up with is instead of having one frame, they have stacked multiple frames. The reason is only then you will know, like if I freeze this frame at one point, we don't know whether let's say at some point, whether the ball is going up or down, because in a single snapshot of the photo, we don't know that. So when they stacked it, then you can know the velocity of the ball, where the ball is moving. So there were tricks like that. Something called as experience replay buffer, which you can think of a short-term memory, right? Something like that was introduced. Clip rewards, just numerical massaging. Target networks. I cannot explain this in the remaining time. Epsilon greedy, a good old approach that we have. All these recipes and tricks, but in my opinion, the resulting solution is really satisfying. Maybe this is not the optimal solution, right? You can say, oh, there's an even better solution. Yes. But in this specific setting where we have infinite input continuous space, right? Like we're seeing images, exactly like how a human does. And being able to even solve it or be able to learn to solve it is itself very powerful, right? And they didn't do. And so let's say once they came up with this tricks and everything, they fixed the algorithm. And then they threw a totally new program, ping pong, right? Or any other Atari games that you've seen. And the agent was able to solve all of them. So that's exactly what the spirit of reinforcement learning is. Can I even learn a solution without approximating the problem? The answer is, well, you can do your prayers, right? And your heuristics, you can. Okay. Okay. I think that's about it, right? There is a part 3, okay, no, I want you guys to have a good evening. So no more equations, but that's about it. All of this is shared with you. Let me know if you have any questions. Yeah. Thank you. You guys still want to do MPC or learning? You will know once you guys do your projects when you try and get into MPC, you will know. Personally, I'm a guy, I couldn't get my kinematics right anytime. I write the inverse kinematics, I do the transformation matrices, I almost always go wrong. That's why I do learning. It has the kinematic problem. But yeah, I mean, both are equally satisfying solutions. Just choose your task, right? Whichever you want to do.
I broke something. Maybe it was like,
where is the attendance?
Is MPPI? just MPC with the stochastic